All right, looks like we are at time. So I'd like to say hello, everyone. Thank you for joining our session on machine learning, climate and weather. Before we get started, just a couple of housekeeping details. One, if you have questions you'd like to address to the speakers, we are using Slido. The link is in the chat. We'll keep reposting that. If you are watching outside of Zoom and don't have access to the chat, you can find the link to the Slido on the conference website. It's under the QR code. You have to poke around a little bit to find it, but I promise it is there. So without further ado, I'd like to introduce Tim Del Sol from George Mason University, who is going to be giving us an overview of knowledge-guided machine learning for weather and climate. Tim, take it away.
All right, and can you see my cursor?
We can.
Okay, all right, great. So I will try to give an overview of knowledge-guided machine learning in weather and climate. This is a challenging thing to do since it's a very active topic. Right now, there are at least 4 journals currently having a special theme issue devoted entirely to machine learning applications for weather and climate, including the prestigious Philosophical Transactions of the Royal Society. Moreover, there's an entirely new journal that's been created by Cambridge University Press devoted to applying data science to environmental problems. Some examples of machine learning. Yes.
Yeah,
Sorry to interrupt. Your screen is black, actually. I saw your screen when you opened your slides, but when you went to full screen, it became black.
Okay.
Yep, can see your title across the top, but not your actual slide.
How about if I, so
there
I don't
you are.
know.
Oh, we had it for a second.
Okay.
There we go.
So I assume you can see the borders.
Yes.
Okay, so I think that's the best we could do. So I'll just go on from here. So this is a list of examples of machine learning applications in weather and climate. And they include bias correction, quality control, data assimilation, subgrid scale parameterizations, and post-processing, and so on. And this is a pretty diverse list, so it would be impossible for me to give an overview of all these topics. So I'm going to focus on a few key issues that will come up in the talks that we'll see in the next 2 sessions. When we discuss machine learning predictions, we can't ignore the fact that there already exists forecasts of weather and climate that are very routine and highly developed. And where do these come from? Basically, they come from the laws of physics. We know that nature conserves momentum, mass, and energy. And the laws of physics are such that if you know the initial state of the system, then the laws tell you how that state will evolve into the future. Now, even if you could solve the laws of physics exactly, you could not make a perfect prediction of weather because the systems are chaotic. By chaotic, I mean that small changes in the initial condition can lead to large changes in the prediction. So I can illustrate that with an actual weather forecast. Here I'm showing a forecast starting on January 1st and going out 17 days later. The specific variable and the location doesn't matter. What does matter is the forecast starts with 21 slightly different values of this variable. For the first 3 days, you see the solutions are close to each other. After 7 days, they're diverging. And then after about 2 weeks, you see that the solutions are completely independent. And if I were to show you a global weather map corresponding to these 21 different solutions, they would all look completely different. So this property implies that we cannot predict the specific weather after about 2 weeks. We can predict only the statistics of the weather after about 2 weeks. And so that's something that has to be understood when doing machine learning predictions of weather and climate. Now, the uncertainty due to the initial condition is not the only source of uncertainty when it comes to weather and climate forecasts. Another source comes from how we solve the laws of physics. When the laws of physics are expressed for fluids, they lead to a system of partial differential equations, which I've indicated here. I'm not going to go through those symbols. What's important is these are nonlinear partial differential equations, and they cannot be solved analytically. And so what we do is we solve them on a computer. For instance, we can discretize the globe into grid boxes and then use numerical differencing techniques to solve the PDEs. The more boxes you have, the more computational power that you need. And under current resources, we cannot make the boxes small enough to resolve all the processes relevant to weather and climate. For instance, convection cannot be resolved in a global model with current computers. Now, a weather prediction that can't include rain is pretty useless. So we can't ignore these processes. So therefore, we parameterize them in terms of the resolve grid. However, there is no completely rigorous way to parameterize subgrid scale processes. The problem is that the fluid dynamical equations are nonlinear, so solving for the statistics leads to a closure problem. And I can illustrate that schematically here, where the variable u is a state variable and its time derivative depends on linear terms and some nonlinear terms. And then when you derive the equation for the first moments, you get a term that depends on the second moments because of these nonlinear terms. And then when you derive an equation for the second moments, you find that depends on the third moments and so forth. And so what happens is you get an infinite hierarchy of moment equations that never close. This is called the turbulence problem, or I'm sorry, the closure problem in turbulence. And some physicists call this the greatest unsolved problem in classical physics. So since there's no rigorous framework for deriving subgrid scale parameterizations, different people make different assumptions in these parameterizations. So even though we start with the same laws of physics, in the end, we have different models because there are different parameterizations. There are many parameterizations in a single global model, and each one involves empirical parameters. And typically, by the time we have introduced the empirical parameters, almost every physical and mathematical constraint that we know has been used. So this is a great area for knowledge-guided machine learning because all of our knowledge has been exploited at this point before we've introduced these parameters. However, these physics-based models are expensive to run. So we can't do backpropagation or make a lot of runs that are customary in machine learning. Instead, we need to use machine learning to develop efficient methods for estimating parameters using a limited number of runs. So there's quite a literature on how to do this. Many methods have been proposed. One recent method that's been proposed is the Ensemble common filter. And on the left side, I'm showing a figure from Schneider et al. In a paper titled Earth System Modeling 2.0, which I highly recommend. And it shows the result of applying the common filter to tune 4 parameters in the Lorenz 96 model. So this model has about 400 variables, which is much less than an Earth system model. And this is what climate scientists would call a toy model that has the same kind of mathematical properties as an Earth system model, but it's much simpler. And data scientists may call this a sandbox model. And the idea is we start out with initial guesses for the parameters with some guess about the uncertainties that's indicated by the shading. And then with each iteration, the common filter estimates these parameters, and the estimates get closer to the true parameter with each iteration. And recently, we implemented a version of this common filter in NCAR's Earth system model, where we use the machine learning technique to choose features and other parameters in the filter. Now, of course, you could apply machine learning without thinking about physics at all. You could just take data and apply machine learning to make a prediction based on a large data set, as is done in many papers. But we can't ignore the fact that there are forecasts available that are based on physics. And so the question comes, are machine learning predictions competitive with physics-based predictions? There are a lot of papers that look at this, but I would say we're in the early stages of really assessing how good or how bad the two types of forecasts are. And of course, the answer is going to depend on what you look at, your time scale, spatial scale, and so forth. But we do have at least one solid reference point. For the past couple of years, the Bureau of Reclamation has sponsored a year-long real-time forecasting competition focused on the Western United States for predicting temperature and precipitation out to weeks 3, 4, and weeks 5 and 6. Now, you are familiar with weather forecasts. These are typically available up to 5 days, but predicting weeks 3 and 4 is a much harder problem. And as I mentioned, the atmosphere is chaotic, which limits what we can predict. Nevertheless, there is evidence that certain weather statistics can be predicted out to a few weeks. For instance, in July, there was a heat wave in the Pacific Northwest. This was due to what's called a blocking event or a heat dome. And although the onset of this heat wave was not predicted weeks in advance, Once it got started, it was predicted to last a couple of weeks, which it did. Other mechanisms that have been identified to give predictability at weeks 3 and 4 include the land surface memory, in which soil moisture anomalies can persist for several weeks, or the stratospheric polar vortex, which can induce changes that last for a few weeks, and some tropical phenomena, such as the Mad-Julian oscillation, which has a timescale around 40 days or so, and can influence weather in North America over those timescales. So when this forecast rodeo competition was run, it turned out that the machine learning models outperformed the physics-based models. And this has happened twice now, and now there's an international competition going on right now by the WMO, the World Meteorological Organization. Now, these competitions are all focused on predictions, which is certainly a legitimate goal, but there's another community that's trying to learn from the machine learning forecasts. In particular, if machine learning can outperform some of these physics-based models, then we would like to understand where that predictability comes from and to use that information to actually improve the physics-based models. So the problem with that goal, though, is that machine learning is notoriously difficult to interpret. There's a huge literature on this topic. Some call this explainable AI. One strategy is to identify important predictors using things like permutation feature importance, saliency maps, and just examining the lasso coefficients. Another approach is to use layer-wise relevance propagation, which will be mentioned in a talk in this session, shapely values, and another approach, using something called predictable component analysis, which will be used in the next, or be discussed in the next section. The problem is that all of these methods have certain pitfalls. One problem is that the machine learning models have noisy gradients between the input and output, which makes them very difficult to interpret. And also, features in weather and climate often are highly correlated, which creates difficulties for interpretation. So to illustrate that, I'm showing an example here in which I predict just one pattern over the US. And the idea is that convective anomalies in the tropics excite Rossby waves that propagate and imprint a dipole pattern over the United States that can persist for weeks to months. And so we can use machine learning techniques to predict the time series of this pattern. And since the pattern is believed to be excited by these convective anomalies, which are tied to the ocean temperatures, we can use ocean temperatures as a predictor. And so what I'm showing here are the regression coefficients obtained from 3 different methods. And the first one has a large scale structure for these regression coefficients with negative loadings over most of the Pacific and positive loadings over the Western basin. And climate scientists would look at this and call this a La Nina type pattern. A second one is a very spotty pattern where almost everything is set to 0 except for a few isolated grid points. And then a third approach gives this very noisy pattern, which I would say is impossible to interpret. Now, despite the fact that these regression coefficients look completely different, they give almost exactly the same prediction. What I'm showing this row here up above each figure is the correlation between the prediction based on these coefficients and the NINO 3.4 index, which is the average SST, average ocean temperature within this box. And you see that each of those correlations are above 0.9. So that means that the predictions are nearly identical to the NINO 3.4 index, which climate scientists have known for 30 years. Yet the regression coefficients look very different. So if the goal is to gain physical insight about the source of predictability from machine learning, this is an example that shows it would be pretty hard to get that insight just looking at these coefficients. So let me return to this problem of the parameterization and mention an entirely different approach to using machine learning. And instead of splitting the globe up into a series of boxes and solving for the whole globe, you can pick one box and then simulate the process just in that box. And usually we constrain certain things in the small box based on information from the global model. But with this model, we can explicitly resolve things like clouds. And we call this a cloud resolving model. And it's not perfect. We still have to parameterize other things like certain microphysical parameters, but there are fewer parameterizations and the solutions are less sensitive to those parameterizations. So here's a snapshot from one of those simulations. And the point here is that these simulations are very realistic. This is a picture you might see outside of an airplane. So the idea then is that instead of training a machine learning on observations, we train them on these cloud resolving models. In addition, we could incorporate other physical or mathematical knowledge we have about the process into the machine learning algorithm. And then we can use this to derive an entirely new type of subgrid parameterization, and then put that into a global model and run. And there will be a few examples of this in the seminars today. So that's the end of my overview. I'm just going to end with the agenda for this, and I'll just stop here. Thanks.
All right, thanks, Tim. I don't see any questions in Slido, but we do have the capability to have the speakers answer questions that come up later. So if you have any questions for Tim, feel free to take those offline. And then I think I will turn it over to Amy.
Sure, we'll give it another minute or two to see whether any questions are coming in. Is there anything else you wanted to share while we're waiting for more questions, Tim? Anything in terms maybe your personal experience of machine learning and how you came about doing more machine learning?
I think the thing that took a while to realize is that when I collaborate with machine learning people, you have to devote a long time to figuring out jargon and getting rid of jargon. And it can often take, hours sometimes to get past that and talk about concepts. And that's part of the process.
Right. So one question came in here. Do the weather forecasts on TV use machine learning for their predictions?
I don't think so. All the forecasts that are done now that I'm aware of are based on, they come from NOAA, Department of Commerce. They're pretty well vetted. Machine learning is a pretty new technology. There might be some recent applications that I'm not aware of, but it would be a slow process to bring them in because people's lives may depend on it. And so you have to have very reliable research backing up machine learning predictions.
I think it's safe to say that at some point that will happen, but it probably hasn't happened yet in the mainstream ones.
Right.
All right. I think with that, we will switch over to the next speaker. So then I'm very delighted to introduce Pierre Gentin, who is a professor of geophysics at Columbia University. Pierre, do you want to share your screen?
Yeah, thanks a lot for the invitation. Is it full screen?
Yes, it is.
Okay. Let me know when you want me to get started. I don't know if you want to stick with the time or.
Well, yeah, maybe stick with the time. We just give it one more minute. And in that minute, maybe you can talk about machine learning and how, your relationship to machine learning, how that came about.
Sounds great. Yeah. Just give me the green light. Thanks.
No, I mean, you could just, while we're waiting 1 minute, you could talk about that right now.
Yeah, so I came along because I basically started developing some new parameterization for convection, and I got really frustrated because I was really happy at first, and then I started to get into the weeds, and I said, I will never get there, at least not within a time frame reasonable for climate change, So, and that's when I started to think, okay, maybe because I was using machine learning on the side for some other things, for like satellite data, I thought, maybe that's the best tool we have right now to actually tackle that within a reasonable time frame, and I just thought that it was just too pressing, there was just too much pressure, timeline was too short, and the development of parameterization was just too slow, So that's where it came from.
That is a great introduction. And with that, I would say, let's start your talk. Thank you.
Thanks, yeah. So today I wanted to talk about, and thanks a lot for the invitation first. I wanted to talk about something I've been really interested in over the last couple of years, is to try to bridge between physics and machine learning. And Tim gave a great introduction as to why we would want to do that, especially the fact that we have conservation laws, but not only. So I will try to explain why we got really interested in that. A lot of that is actually work from Tom Buckler. He was a former research scientist in Mike Pritchard's group and my group. He's now at University of Lausanne. He has a lot of offers right now, so please look him up. And Stefan Rasp also in Germany, in a startup right now. So really, what I wanted to discuss today is really looking at the hydrological cycle and looking at clouds and convection in particular. And Tim gave a great introduction to talk about those things. And the reason why I got interested is when we start thinking about climate change, a lot of the projection that we get from climate models is really, really uncertain. And a lot of those uncertainties is basically related to small things like clouds, and what it means is that those small clouds that we cannot directly resolve because the models are really coarse, actually strongly regulate actually the global temperature change for a given amount of greenhouse gas concentration. And that's some nice work by Tapio Schneider and Florian Briand, looking at what will be the response of basically what we call climate sensitivity. So that's basically the equilibrium temperature of the planet for a given amount of CO2 concentration in the air. And you can see that every circle here is basically one climate model. And you can see that there's actually a vast variety of different answers in terms of what will be the, if you will, on the x-axis is like the inverse of temperature for a given amount of CO2 concentration. So there's this really wide range, and you have some models that are very aggressive. It means that you will need to have very low CO2 concentration to reach a higher temperature, and some models that are a little bit more optimistic, saying, okay, you can actually go a little bit further in terms of CO2 concentration, you can emit a lot more, and then the planet will be actually a bit cooler. And actually a lot of that can be directly related to clouds. And in fact, here that's related to low cloud reflectance. And in fact, it does make sense. I mean, the more clouds you have and the brighter they are, the more reflection you will have back to space, and therefore the cooler the planet will be. So you will have this kind of damping effect, feedback, as we call it, as opposed to some amplifying feedback if the clouds were to be fewer or if they were to be darker, basically. So they are absorbing more. Okay. So what it means is that that feedback is actually crucial to understand and project the change of the global temperature, but not only temperature, also the water cycle and all sorts of things like droughts and heat waves and all sorts of things that are responding to climate change. And that's basically a lot of what is actually controlling what is here in the red box, which is the Paris Agreement. I mean, the IPCC just got released today, the report. And so we typically use 2 degrees as global temperature warming compared to pre-industrial. And you can see that's basically related directly to the amount of CO2 concentration you will have. And that's vastly varying across climate models. And that's really a major roadblock for policy making and a lot of the impact we want to have as a community. It's not just a global issue that we have here, it's also very much at the regional scale. That's some really nice work also by Sandrine Boni and Bjorn Stevens, looking at what would be the impact of regional radiative effect and precipitation for 4 degrees of warming. So in that case, what they did is they took what we call an aquaplanet, so just ocean everywhere. You bump the temperature of the ocean by 4 degrees, and you just want to see what will be the response of the climate. And every column that you have here is basically a different model. And you can see that it vastly differs across different models. So some models are going to see an increase in precipitation in the tropics here, a drying in the subtropics, and you could see the converse, almost the opposite, if you take another model. And the issue is that what we typically do is we take the multi-model mean, and that will be the best prediction or the best projection you will have. But of course, maybe only one of them could be right, and the other ones could be completely off. And again, that's a major issue because what you would want to predict or project is going to be the regional hydrological cycle change, right? You want to say, will we see more droughts? We will see an intensification in extremes and precipitation. So those are things that are crucial for people to basically to adapt to climate change. So we need to give a much more accurate type of response. And as you can see here, in that case, we are purely forcing the atmosphere. So it means that a lot of that variability that you saw here in the first slide and the second one is actually just due to like some very small scale processes in the atmosphere. And that's what we typically represent using a so-called parametrization. So that's what Tim introduced before. And that's basically a subgrid representation of things that are basically too small to be represented at the scale that we have in a climate model. And a typical scale will be roughly 100 kilometers or so. And so a lot of those clouds or convection, so deep clouds that are typically precipitating, will need to be represented in a statistical sense, right? And they will need to look at what will be the mean effect of those onto the grid. And you can frame that in terms of a closure, as Tim said, but if you look at the rate of change, we typically write that as a tendency. What is the change in some particular variable. It could be temperature, moisture, or something, or some scalar or momentum, and what is the rate of change that's due to clouds or convection or something else, or turbulence, okay? And that should be just a function of things that you're resolving at the core scale, so just the grid average, okay? The grid average temperature, the grid average moisture, et cetera, okay? And what we do is we do that typically using a physically based approach. So we have some mechanistic understanding of clouds, of convection, of turbulence, and we are trying to represent that directly onto that grid, right? But the issue is that a lot of the spread you saw earlier is actually just coming from the diversity and the zoo of basically parameterizations we have, and even sometimes some fine tuning of some of the parameters for the exact same parameterization can actually lead to vastly different responses, okay? And that's led to what we call some sort of roadblock or deadlock in the so-called parameterization, as Dave Randall actually showed back in 2003. Okay, and that largely explains the intermodal spread in climate projection. And that's a major, major issue that we need to solve as a community. So what we thought like a couple of years back is that maybe a way to tackle that would be to use cloud resolving models, so simulations that are roughly of the order of a kilometer or so. And we know that those simulations can actually resolve clouds or deep clouds or convection relatively well, okay? And they resolve many of the biases we have, such as the diurnal cycle. They can have some sort of mesoscale convection. They have convection at the right place. And so maybe what we could think of is basically using those and learning from those simulations, even though they might be just over a short period of time, and using them as kind of a template for how we should actually deal and represent convection in a coarse resolution model. Okay, and that's one example of such a cloud resolving simulation. So that's basically what we decided to do. And so we took some cloud resolving simulation. If you want it to be precise, it's actually just a 2D. We can get into the details. No need to get into that here. But basically, you have a cloud resolving simulation, so fine scale resolution simulation. You coarse grain that to the scale of the climate model, so roughly 100 by 100 kilometer. And then what you do is that at that coarse scale, you actually learn basically the salient features of convection, right? You want to say, what's the tendency of temperature or moisture as a function of things that I'm resolving at the scale of the large scale grid, right? So basically you will have as an output the rate of change of temperature due to convection, so deep clouds again. Moisture, so Q is specific humidity, as a function of temperature, moisture, so specific humidity here, and you also have like surface boundary conditions, okay? And you could use many different approaches. Again, you could use a physically based approach. In our case, we said, let's learn from those cloud resolving simulations, and let's build that link and that statistical relationship using a neural network. Then we use some other ones. But basically, you can learn that relationship, and you can fit those neural networks on those simulations. Okay, so it's basically a data-driven approach as opposed to a physically based approach. And when we compare that to the actual fine scale simulation here, again, coarse grained, which is at the top here, you can see that we are doing a pretty good job. So here is precipitation at the surface, outgoing long wave radiation, just to up to 2D snapshots. And you can see that basically there's a very good correspondence between the two different simulations, the middle one here being the neural network representation of that. We call it cloud brain, okay, or C-brain now. And you can see at the bottom the difference between the two. So you can see that there's pretty good agreement in terms of where is the location of precipitation and where is the intense precipitation going on. Okay, it's not perfect. You can see there are some spikes. And in fact, if you were to look into that, you can see it's actually very much stochastic. And you can see that the field we are actually getting from the neural network is too deterministic in a sense. It's too perfect, right? So we would want to add a little bit more noise. Okay, but that's something that needs to get into. The advantage is that we are way cheaper than the high resolution model, so roughly 10,000 times, 1,000 times. But we're also even cheaper than the coarse resolution model because it's basically a bunch of matrix operations. So it makes it even cheaper than the original parametrized convection system. Those were based on individual snapshots because we, as Tim said rightly, I mean, then simulations will diverge if we were to initialize them differently. So at every time step, we are actually comparing what will be the impact of the neural net as opposed to the actual high resolution simulation. But we also coupled directly the neural network. So we took off the regular parameterization and plugged the neural network and said, okay, what will be in that case the impact? We cannot track individual trajectories, again, because the flow is chaotic, as Tim said. But what we can do is we can compare statistics, right? So we can look, for instance, at extremes of precipitation or distribution of precipitation. And what we found in that case is that the neural network, which is here in red, was compared really favorably to the high resolution simulations, which is here in blue, okay? And also doing a much better job than the original physically based parameterization, which has the typical, what we call drizzle problem, where precipitation happens too frequently and also tends to be too weak. So we don't have enough extremes of precipitation, and that's a major issue when you want to look at the water cycle in particular. Yeah, so we thought that was good news. We're actually excited. We also looked at wave propagations. We were really excited, and then the issues started. Okay, so the first one was the first issue we found was really one of physical constraint, right? So we started looking at the energy balance of within like different columns, and you can do it across the globe. And here are different, basically samples from those different grid cells. And you can see that those are different budgets. So the simulated energy balance as opposed to the actual one. And you can see that we are pretty much on a one-to-one line. So it's pretty good, right? It means that the neural net has kind of learned that there was an energy conservation, but it's not perfect, right? And in fact, you can get deviations of sometimes like hundreds of watts per square meter. And that's a major issue because climate change is a few watts per square meter. So you would want to be like perfect, right? I mean, you want to be spot on and you cannot lose energy. So it means that even though we are doing a decent job in terms of like spatial and temporal representation, we don't have energy conservation and we don't have mass conservation, and they only approximate with the algorithm. The second issue we found that's a major roadblock as well is one of generalization. And what we did is what we basically did the same experiment I showed you before. You take the ocean and you bump the sea surface temperature by 1 degree Kelvin, 2 degree, 3, and 4 degree. Okay, and you can see basically the expansion here of the circulation and the contraction here at the equator. And we said, okay, can the coarse resolution neural network actually replicate that in the online simulation? And what we found is it just failed miserably. In fact, it failed the very same way that many parameterization do, using and having basically a double ATCC, the typical issue that many physical parameterization have. Okay, so we're really disappointed when we saw that. We say, okay, basically that's a major roadblock because it means that what we learned in the historical climate cannot be used in the future and basically defies the purpose, right? So that was basically a major roadblock we thought at the time. And then we just wanted to know, is it a purely extrapolation issue or would it be something else? Is it more of an interpolation issue? And so what we did is we trained on like historical climate, so 0 Kelvin and plus 4K, so basically the future, but really warmer. And we said, if we know those two climates, can we interpolate things in between, right? And that's basically what you will have at the bottom, and it does a pretty good job, right? So it's really showing that it's really an extrapolation issue and not just an interpolation one, right? So you need to kind of extrapolate better, and you at the same time need to conserve physical laws, right? So some summary of the issues, basic machine learning algorithms on your nets in particular do not respect physical laws such as conservation of energy and mass, but those are strict requirements for climate change. And there's also issue with out of sample generalization, right? So as long as you stay within the range of prediction, you're in good hands, and those algorithms work really well. In fact, they're hard to beat, as Tim said. But as soon as you're like out of sample, and climate change is all about out of sample prediction, the issues start, right? And extreme events are another type of similar issue where a lot of that you've never seen before, especially of the scale. I mean, we're seeing that on a day-to-day basis now. So you could think of that, maybe one way to tackle that would be, what if we were to actually influx a little bit of the knowledge we have, right? We are not in the dark, right? I mean, we have years and years or decades and centuries of knowledge, of physical knowledge, and maybe we could influx some of that, right? So the typical machine learning algorithms are really sitting here, right, on the left-hand side, where you have so much data, but also you're really staying within the same distribution that you can just deal with the data, and that will do an amazing job, right? And we are seeing that on a day-to-day basis, with many of the machine learning algorithms we have. But what I'll discuss in the rest of the talk is when we actually are missing some data, either on the extremes or there's a shift in the distribution. So how can we actually deal with that by using some of the physical knowledge that we have? And that's what we will refer to as a hybrid type of modeling. Okay. And sometimes you can be really data poor. So you're also like undersampling. So you also have some sampling or selection bias. So I won't discuss that today, but so let's focus mostly on like when we are actually missing or there's a shift in the distribution. So the first thing we can do is actually trying to constrain some of the physics, right? So we have some physical laws like energy and mass conservation. But what we could do is we could actually directly bake them into an algorithm, right? So you could take your network, which is here in blue, and you could say, let me add some layers, right? So you would have some hidden layers. And those hidden layers will actually be every time, every layer will be, additional layer will be a conservation law. Like you will have one for some mass conservation, one from some momentum conservation, and you keep adding them. And instead of training on your network and then trying to tune that, you could actually train the whole thing end to end, right? So you could say, I'm training my neural network, but also imposing some layers that are combining different inputs that I'm using from the different previous layers. And I'm combining them in a way so that I can train the whole algorithm end to end. What it means is that you train your neural network, so the data-driven part, but at the same time, you're always conserving energy and mass or whatever conservation laws you have at the same time, because it's again baked within the neural network. And it works really well within numerical precision. So if you're interested, Tom just published a paper on that in PRL, and really it works well, and you can have nonlinear functions and things like that. So that tends to work pretty well. The second issue we wanted to tackle is one of generalization. So we say, okay, let's go to a very extreme case, right? Let's go to a +8 Kelvin experiment. And what we would want to do here is we would want to say, can a neural network train on historical data, be able to actually predict or project the future? So the truth here would be that's going to be the moistening here in the some latitudinal average. And that's going to be the heating rate, again, over some latitudinal band, doesn't really matter what it is. Okay, so moistening and heating, those are the targets we want to have in the warm climates. Okay, so those are the anomalies. So if you just use a neural network trained on historical data, you will get that. Okay, so you will get something that's completely off, and that's what we saw earlier in the talk. Basically, you're failing miserably. Okay, it doesn't work at all. Your moistening is like just orders of magnitude and sometimes even in the wrong direction. So it just doesn't work. Okay, so something is fundamentally flawed in the way, so in fitting a neural network on historical data. But what if you start using a little bit of your physical knowledge or some of your physical understanding? So what we know is that humidity is not going to be conserved, right? We know that the holding capacity of the air is going to actually increase with climate change. But what we do know is that relative humidity is bounded, right? It's between 0 and 100%. And what's going to bound that is the saturation water vapor, right? So if we are now starting to use relative humidity as opposed to specific humidity, even though those are correlated, you could say, in fact, it's doing directly a very much better job. So that's going to be the result you're going to get here in terms of the moistening and heating, right? So right away, by just adding a little bit of physical intuition, you're actually getting much better result and much better generalization. You can actually get to some additional physical knowledge. You can add, that's not the right wording now, but you can add buoyancy. We know that buoyancy is actually very important for the parcels in the air and for the updrafts. And you could do some rescaling as well. So instead of using temperature, which we know is actually shifting with climate change, you could use buoyancy, which is just an anomaly compared to the surrounding and the environment. Okay. And when we do this temperature or buoyancy rescaling, we're actually getting even closer to the truth, right? To the projection in the future. And that's in terms of the input, but you could also do the same for the output as well, right? You could say the fluxes, the output are also going to change, but we could also rescale that based on, say, the surface fluxes that we are actually projecting as well. And that's going to get you even closer to the end result, right? So what it means is that by adding some physical constraints or physical intuition, you're getting closer and closer to something that's basically climate invariant, right? So something that will actually work, even though it's only trained on historical data. And that's very useful if you wanted to use for instance, satellite data, or something that cannot be generated in the future, or where you don't know the processes in the future. Okay, so a quick summary of that would be, you have your original PDF, say, in terms of humidity. You would want to rescale that in terms of things that are relatively distribution invariant. And if you were to directly use the brute force mapping here, what you will find is that the PDF are fundamentally shifting in terms of the output. But if you use the climate invariant mapping, in that case, the PDF, the rescale PDF will actually be almost unshifted. So that's the intent, right? You're not doing any sort of out of sample prediction, and that's the ultimate goal, right? So going to influx and physical knowledge, so you avoid that shift in the distribution. Okay, so quick conclusion. So machine learning is really appealing, as Tim mentioned, for climate processes, and in particular for representing physical processes. And I hope I showed you some example where it works for deep clouds, but again, there were some issues related to conservation and generalization, right? And physical invariance. So those are things we want to tackle. And I hope I convinced you that if you were to actually bake in some physics directly into the structure or the architecture of the neural network, or by having some physical knowledge based into that, then you can actually tackle many of those issues, we hope. Okay, with that, I'll finish. And if you're interested, we also have one example for evapotranspiration with the same type of approach. Thank you.
Thank you so much, Pierre. So we have one question aside, that is there a diagnostic that will tell you when the machine learning is in extrapolation mode rather than interpolation mode? It is not obvious since it is multivariate.
Yeah, that's actually a great question. Yeah, so actually the way we do it is mostly with the marginal, so mostly univariate, but that's true. Yeah, it's not straightforward to directly do it in the multivariate, especially when you start going to higher and higher dimension. Yeah, that's a very good point. If we had a way to do that and test that, and you also need to have the right data to test that. So in our case, we're in good hands because we can actually generate some like artificial data, but if you don't know that a priori, that can be tricky. I mean, you could use a colder climate that from the past, as a way to test that. But those are, yes, very good questions. Yeah, I don't have like a recipe, let's say. Yeah, we are doing that as we speak. And Tom will have the paper out soon, so it will be on archive. So if people are interested.
And that's Tom Buchler. Okay, now questions keep popping in. Next question is, what is the meaning of brute force mapping and climate invariant mapping? Are they implemented by physical models or data-driven model?
So by brute force, what I meant is a pure machine learning algorithm just trained using some data. So basically, you give the problem to a computer scientist that wouldn't have the physical knowledge, right? So they would just say, okay, give me that input data, or input features, those input features, and I'm gonna give you the output. And it seems to work well on some specific data set, which is basically the current climate. But it does fail when you start looking at future climate, right? For the reasons I mentioned, because in fact, there will be a shift in that distribution. For instance, temperature is going to be warmer. The humidity is going to be way more humid or higher. So implicitly, there's going to be a shift. A climate invariant is basically using some physical knowledge where we know that relative humidity is basically not changing dramatically across the globe, where buoyancy is going to be in terms of the anomaly. So those are things that are not dramatically shifting. So we know that we are actually baking some constraint in terms of the range that we have,
So we have 3 more questions, but I think we probably only have time for one. So I will pick the first one. Can you clarify how you include RH? I guess that's relative humidity. Did you add a constraint layer for RH or just as an input variable?
Just as input variable. So there's just an additional variable where you have temperature, humidity, you go into relative humidity, pass it on to a neural network, and then you can go back to because at the end, what you want is you want to have the tendencies in terms, again, of the same thing as before in terms of, in terms of temperature, right, which was the original variable. So you need to go back to the original variable. So there's just a little bit additional work to get to those climate invariant variables, and then you go back to the original ones that you wanted to predict, because they are the ones that are in your climate model in particular, like temperature, specific humidity, or it could vary depending on the climate model.
Great, thank you. There are 2 more questions in Slido. Maybe you can go in there and put a reply there. Sure. With that, thank you so much, Pierre, for your talk, and I will turn back.
Thanks.
I will turn it back over to Ben.
Thanks so much.
Continuing the tag team. So our next speaker is Katie Diggin. I hope I'm pronouncing that right, from the National Center for Atmospheric Research. We'll be looking at precipitation extremes. Take it away.
Thanks so much. Hope you can see that. Okay, just give me a shout if not. So yeah, thanks to the organizers for the invitation to speak. My name is Katie Diggin. I'm at the National Center for Atmospheric Research, and I'm going to talk about some work where we've been leveraging machine learning-based feature detection algorithms to identify synoptic weather events, but also to then associate those detected features with extreme precipitation. And this work is in part funded by the Department of Energy through a cooperative agreement at NCAR called Catalyst. So the motivation here is that we know that extreme precipitation has significant consequences. I'm showing some examples from a couple of years ago, but we've already seen many examples this year. I think someone in the morning session mentioned the extreme flooding that we've seen so far this year. But we also know that extreme precipitation comes from many different sources. So I'm showing on the right an example of some of the flooding after Hurricane Harvey, so tropical cyclone, extreme precipitation. But then on the left, I'm showing an example of the Oroville Dam spillway overflowing a couple of years ago after an atmospheric river event. And if you're not familiar, atmospheric rivers are sort of these long bands of moisture that sort of transport moisture and precipitation from the tropics to the mid-latitudes. So we'd like to be able to better understand and distinguish different sources of extreme precipitation, and also think about how the mechanisms for them might change with climate change. So as I mentioned, we're going to leverage some of the work on machine learning for pattern classification or feature detection that's sort of been well developed over the years. And so some of the particular goals of this project are to apply and develop different machine learning based detection algorithms to automate the classification of synoptic weather features such as atmospheric rivers, tropical cyclones, and fronts. And I'll spend the first part of the talk talking about atmospheric rivers and tropical cyclones. And then the second sort of longer part, we'll talk about the frontal detection work that we've been doing. But then also kind of bringing it back to the motivation, studying the causes of extreme precipitation by associating those features with extreme precipitation events. And because this is KGML, I'm going to try and sort of highlight examples where we utilize a knowledge-guided approach to machine learning for this work. So to start with the detection of atmospheric rivers and tropical cyclones, we're leveraging an existing project called ClimateNet, which is based at Lawrence Berkeley National Lab. And we're collaborating with Karthik Kashnas and Arvind Nayak on this work. And so what they've done here is created this really unique community-sourced, expert-labeled data set to detect atmospheric rivers and tropical cyclones. So what I mean by that is they've actually gotten experts to hand label from climate model output tropical cyclones and atmospheric rivers in order to build a training data set for a machine learning detection algorithm that can be then used in an inference state to detect these features in other data sets. And so if you're interested in the sort of nitty-gritty details of the machine learning model, I would refer to you to this recent paper, Prabhat et al., which talks a lot more detail about the training and the architecture. But I do want to just mention the sort of uniqueness about this data set in that it is based on expert labels. And there were several sort of labeling campaigns that they held within the past couple of years. We held one at NCAR back when we were in person in 2019. And so this animation is kind of going through how these expert labels are collected. So the tool samples a random time point from climate model output, because again, that sort of serves as the baseline information for the training data. But the user can toggle between different output fields, for example, water vapor, pressure, winds, whatever knowledge or information is most useful to categorizing these events. And then the expert actually goes in and draws boundaries, like the animation is showing, around a particular event, labels it as either an atmospheric river or a tropical cyclone. And then kind of interestingly, I think from an uncertainty quantification perspective, is also able to add their confidence level in terms of whether they are sort of low, medium, or high confident in the classification of a particular event and also the bounds of that event. So our question was kind of seeing how we could leverage this existing trained model and use some of the simulations that we have at NCAR. So in particular, Community Earth System model, which has already been mentioned a couple of times, CESM simulations that were run at high spatial and temporal resolution. And the high temporal resolution is really key for capturing these dynamic features. But the question was, can we use the pre-trained algorithm applied to climate model output and still detect these features? And so this animation is showing that we've been able to have success with that. So here I'm showing labeled atmospheric rivers in red and tropical cyclones in green. And this is from the CESM model output run through the trained algorithm. And if you're interested in the particular fields, I'll talk about this a little bit on the next few slides. It's using vertically integrated precipitable water, sea level pressure, and UV winds at 850 millibars. And so then it outputs either sort of a classification label spatially for atmospheric rivers, tropical cyclones, or none. There's a couple interesting things to point out here that will lead me to the next slide to talk more about atmospheric rivers, but you'll notice there's a tropical cyclone feature here that as it evolves over time kind of seems to morph into an atmospheric river. And so that's kind of an interesting question where we might be able to look more into the genesis of atmospheric rivers and how they form and how they evolve. But in particular, because we're able to detect these atmospheric rivers, we wanted to bring in some knowledge from another related project, which my colleague Christine Shields at NCAR is one of the leads on, and that's the ARTMET project, or the Atmospheric River Tracking Method Intercomparison project. And so this is a project that is trying to understand the differences in atmospheric river science based on detection algorithms. And so this plot on the right, I'm showing from a recent paper comparing many different atmospheric river detection algorithms. And they were developed for slightly different purposes. So it's not all that surprising that they sort of vary in their sort of spatial extent or definition of an atmospheric river. But what's interesting from our perspective is that many of these detection algorithms are based solely on, often solely on a single input field, so integrated water vapor transport, or IVT, shown here. While the detection methods might vary in other ways, for example, using absolute versus relative thresholds, a lot of them are just based on IVT. And so with this sort of information in mind, we wanted to go back to our detection that was trained on 4 input fields and sort of ask the question, do the results change when altering the input fields? And so in fact, when we repeat the training for a single input field, just the vertically integrated precipitable water, we're still able to detect ARs. We're not able to detect TCs, but we're still able to detect the atmospheric rivers with similar spatiotemporal representation as the model trained on all 4 input fields. And I want to just give John Truesdale a shout out for his help retraining the algorithm here. So that's kind of a nice example of using the machine learning in a knowledge guided approach. It's also a nice example of transfer learning because we're able to apply these pre-trained algorithms to different climate model data sets and also to kind of mix up the input fields and see sort of what the results look like. So that's all I'm going to say about the atmospheric rivers and tropical cyclones. I want to spend the rest of the talk talking about a different detection algorithm, which was designed to detect different front types. And so for this work, we're collaborating with Jim Baird and Ken Kunkel at NC State. And they developed an algorithm called DL front, which is based on detecting different front types. And the input fields are a little bit different here. So they're looking at surface fields, surface temperature, sea level pressure, specific humidity, and surface winds. And then actually outputting 4 different frontal categories, so cold, warm, occluded, and stationary, as well as the none sort of background type. And in their paper, which has a lot more details on the type of the machine learning algorithm and the architecture and things like that, but they are able to successfully detect about 90% of manually labeled fronts over North America. A couple of things to note here. The spatial domain is now just North America versus what I was showing with ClimateNet, which was a global spatial domain. And the reason for that is really based on the training data set. So again, kind of one of the challenges with these sort of detection algorithms is where you're getting your training data. And so for this front detection, they were able to leverage a human labeled data set from the National Weather Service that I'll talk more about on the next few slides. But it was limited spatially to North America. So hence the reason for the change in spatial domain, but again, sort of importantly, able to use those human labels of fronts to be able to validate the performance of the front detection. And so our question was, again, can we use this pre-trained algorithm applied to our CESM output to detect weather fronts? And again, we're able to do that, and we're able to distinguish between the different front types in the CESM output. But I wanted to kind of take this a step further and sort of ask the question, how do we validate these results coming out of CESM? How do we know that the detected fronts actually make sense in terms of real world perspective? And I mentioned earlier that we have this human labeled data set. It's called the National Weather Service Coded Surface Bulletin, or CSB. But now that we're sort of comparing a human labeled front data set to climate model output, it's less useful to just look at a random time point and compare the front locations, because we wouldn't expect the climate model atmosphere to perfectly represent the real world at that particular time point. These are fully coupled climate model simulations. So what we can do, though, is we can look at statistics over time and sort of compare the detected fronts in the two different products on sort of a larger scale. And so that's what I'm showing here. I'm going to show a couple of slides that look at seasonal front rate crossing climatologies. And so what I mean by that, sort of looking at how often fronts pass across the North American spatial domain. And so calculating a sort of spatial mean front crossings per week, and then looking at that seasonally. And so we're comparing the climate model results from CESM in orange with the validation data from the Coded Surface Bulletin in blue. And so we can see that there's pretty good agreement across all of the available years that we had, which was limited by the CSV data set. So pretty good agreement across the different seasons, well within the standard deviations for those two data sets. We can also look at this spatially. So again, this is kind of taking a step back and not doing a spatial average, but looking at the contiguous United States and just comparing the spatial patterns, which again look pretty good. I should note here that I've combined all the front types into just all or none, but we can also look at that sort of breakdown by front type. As I mentioned before, the detection algorithm is able to distinguish between the different front types. And so if we do that, we see that there's slightly less good agreement for the warm fronts and the occluded fronts, though these are overall less frequent if you sort of compare the y-axes for these different plots, whereas the sort of total front crossing climatologies are more dominated by the cold fronts and the stationary fronts, which do show very good agreement, mostly within the standard deviation across the models and the observations. But we wanted to go a step further, do some further validation of the CESM output. One of the reasons for this was that we had to kind of adjust the input fields that we were using from CESM, purely based on the fact that some of these high resolution simulations do not have all the input fields saved at 3 hourly temporal resolution, which is what we need to run through the detector. So what we did was we also wanted to compare to some reanalysis data where we did more apples to apples comparison, and we tried to use the same input fields from MERA and from CESM. The difference here is that they're both run through the front detection algorithm. So unlike the previous comparison where we had sort of a ground truth observations with the climate model, machine learning detected fronts, these are both products that are run through the machine learning algorithm, but it can still give us some sort of more insight into the skill of the front detection. And it's really a more feasible alternative than having to go and hand label fronts in CESM itself. So again, we're showing good agreement for sort of a 16-year climatology that I've pulled from MER reanalysis and CESM. If we look spatially, we continue to see some good spatial agreement in terms of the peak of the magnitude is sort of in the central US. Perhaps CESM may be slightly underestimating the front detection in sort of that sort of peak magnitude relative to MERA. But in general, we're seeing pretty good agreement. So given that we have done all this validation and we feel pretty confident in the detection, we can then sort of move to comparing the front detection response for two different climate states. So here I'm showing both CESM, two different simulations with a present day climate and a future climate with RCP 8.5 foreseen at the end of the century, and comparing the climatologies again. And we were surprised to see that they're actually pretty similar. Looks like maybe there could be a drop in JJA that I'll talk about more in a little bit, but overall not seeing very significant differences, at least for this particular metric of sort of spatially averaged front crossing rate climatologies. Again, if we look spatially, we do see some differences in the spatial patterns with season. And it does seem like there could be a decrease or potentially northern shift in JJA with climate change that I want to dig into a little bit more. So I'm going to show you instead the difference plots, which just makes it a little bit easier to compare the plots on the previous slide. And again, it does look like JJA shows a decrease in the detected fronts, more so than some of the other seasons where you see kind of a mixed response spatially in Northern Hemisphere winter and spring, and then less of a response in the fall. So again, I want to kind of bring in some knowledge-guided approach here. We were thinking of possible mechanisms responsible for a decrease in detected fronts with climate change in the summer. And so we actually were thinking about the response of the jet to climate change. And so I'm showing here actually some work from one of the workshop organizers, Libby Barnes and Screen 2015, looked at the jet latitude response of the North Atlantic jet shift under climate change. So these are from CMIT models looking at the response to RCP 8.5, future climate response, and looking at that with by season, by month. So what you can see is, while the response is a lot less certain in winter, and this is still a very active area of research, it does indicate that there could be a northward shift of the jet in the summer, and that could be responsible for this decrease in detected fronts. However, we don't really see that decrease as much in the fall, whereas we might still expect to see a shift in jet latitude. So this is something that we need to dig into a bit more, and also to try and test this response in other climate models and other CMIT models, and see if the climate change response is consistent. So in the last couple of minutes, I want to bring it back to the beginning and talk about how we actually connect these detected features to extreme precipitation. And so here I'm just showing a snapshot at a particular time point of 90th percentile precipitation from the climate model and the detected fronts. So basically what you can see is there are some places where the extreme precipitation lines up with the detected fronts, and then there are some places where it might not, indicating possibly another source. So we wanted to dig into this and quantify this instead of just looking at a particular time point, a random time point. And so I'm going to walk through the sort of steps we took to do that on the next couple of slides. So we started with precipitation output from the climate model. And this is where it's great that we have this large data set of climate model output, because we can actually compare the precipitation from the same time period and the detected fronts. So we start with the precipitation field. We pick out the grid points that are greater than the 90th percentile precipitation for the particular time period. We then compare that to the detected fronts for a particular time point, and sort of ask the question, which of those extreme precipitation grid points are associated with a front? And here I'm just doing it by lining up, which grid points overlap, but there's probably lots of different ways we could look at this. In addition, there's lots of different ways to define extreme precipitation, so that's something we're going to think about as well. But if we sort of look at this sort of snapshot, and compare the percentage of grid points that are associated with a front relative to the total extreme precipitation grid points, we can then actually start to look at some large scale statistics. So this is a plot showing the percent of, here PEX means extreme precipitation, percent extreme precipitation grid points associated with the front for the sort of present day CESM simulation. But this is looking across all of those years and taking a climatological monthly mean. So you can see that there's a strong seasonality to that, where it's higher in the winter, lower in the summer. If we look spatially, we can also see some differences where there's certain regions of the US where the precipitation extremes are more dominated by a front. Then we can also compare to the future climate simulation, where we still see that strong seasonality, but possibly a decrease in the precipitation extremes associated with fronts. And I'm going to show you the difference plots to make that a little bit clearer before I wrap up. So this is the difference in seasonality, where you can see it's negative, so it's a decrease in all seasons with RCP 8.5, more so in the winter. And then kind of an interesting dipole response, which we're still trying to sort of dig into spatially in terms of decreases in the eastern US, but maybe some increases in the western US. Now, part of this could be that we saw that there was a decrease in fronts detected with climate change, but we also have to dig into the response of extreme precipitation to climate change. And finally, we'd also like to repeat this analysis for the atmospheric rivers and tropical cyclones in order to understand how those features are responding to climate change. So I think I will end sort of quickly with these few summary points. I know we want to get to questions. Sort of talked about all these main conclusions, and then just talking briefly about some next steps. I've talked about some of these, checking the response to other models, the resolution dependence, applying explainable AI, which I know is the subject of a lot of the talks here. And I'll just leave it at that. Here's my contact information. Thanks very much for your attention.
All right, thank you very much. We do have a few questions. I'm sure more will come in. The first one is, I'm wondering if the ClimateNet tool is available for the public.
Yeah, there's a link on the slide where I showed about ClimateNet that you can go, and I think it's possible that the tool is still collecting data. I'm not sure, I'd have to check with the the leads of the project, but there's also the paper that I mentioned that sort of reports some of the preliminary results. And hopefully, more papers to come. So I would, I know these slides are going to be posted, so I would just check out that link that I had for the ClimateNet project.
See, the second question is mine, so we'll skip that one for the moment. The other one is, in the DL front model, what's the rationale for using a constant number of filter maps? Why not an expansion type?
Yeah, that's a great question that I don't know the answer to. I would refer you to the publication that I mentioned that really goes into the details of the architecture and why various choices were made. I know it's a CNN architecture, but I'm not familiar on the nitty-gritty details of the architecture. So that's the Byard and Kunkel 2019 paper.
It looks like we've still got a minute, so I'll ask mine. So for the front detection work, were the inputs picked a priori, or did they emerge from the analysis as the best inputs for identifying fronts?
Yeah, I think it was a combination of the two. I think there was some testing done, but once they sort of settled on the surface fields, and again, just what data was available, and that's a challenge we've had applying this to the climate model simulations. Do we have the right output fields available at the right temporal frequency? So we've had to be a little creative, especially with humidity, by swapping in some alternate fields, and also even maybe using 6-hourly data instead of 3-hourly data. But it's kind of a nice test of the skill of the algorithm that it's able to still detect fronts even when we have to make these sort of substitutions.
Okay, thanks. Maybe time for one more. Do the detection algorithms know the geographic location of the extremes, or is the detection based on relative features that are invariant to translation?
The detection algorithms do not know the locations of the precipitation extremes, except that they're getting, related input fields, I guess I would say, like for the CESM example with the fronts, it's just getting, surface temperature, humidity, winds, and pressure. And so the fact that we sort of independently then look at the precipitation output from CESM, we're able to see some overlap in those features, but the detection algorithm itself isn't seeing precipitation directly.
Great. All right. Thank you very much. It looks like there are probably a few more questions will trail in. If you want to tackle those in Slido, then we'll turn it back over to Amy.
Thanks.
Thank you for the talk.
Thank you very much. And now it is my pleasure to introduce the last speaker before the break. And that is Peter Dubin, who comes from the European Center for Medium Range Weather Forecasts, also known as ECMWF. And he's going to talk to us about challenges when preparing machine learning tools for use in operational weather predictions. Take it away, Peter.
There's the unmute button. Yes, thank you very much. It's a pleasure to be here. Thank you very much for the invitation as well. So I'm going to talk about the challenge for operational weather predictions, and I'm working at this the institute with the strange acronym ECMWF. And I just have one slide to give you a very quick introduction into what we are and who we are. So we are the European Center for Medium Range Weather Forecasting, and we are a research institute, but we're also a 24/7 operational weather service. And we're focusing on global weather predictions, and in particular in what we call the medium range, so a couple of days into the future, but also all the way to monthly or seasonal forecasts. And we are based in Reading, which is in the UK, somewhere around here. But now we also have two more sites. One of them is in Bologna in Italy, and the other one is going to be in Bonn. And as we do operational weather predictions, we also have supercomputers. So high performance computing is quite important for us. And we're also building our own global weather prediction system, which is called the Integrated Forecast System. So given that we are an operational weather center, I thought it would also be useful to kind of at least briefly talk about why machine learning could be interesting or also dangerous for operational weather predictions. So the reason why it's interesting is that there are a lot of applications for machine learning across our workflow at ECMWF. So this is a figure that shows you or tries to show you and visualizes the workflow that we have. So we take observations that are coming in, and then we perform data simulation where we bring observations and the forecast model together to generate initial conditions that are kind of both close to the observations, but also meaningful in terms of the model state. Then we run our numerical weather prediction forecast into the future, and then we have post-processing and dissemination, where you basically get the model output and make useful products out of it. And underlying, there's this big high-performance computing and big data processing chain that is basically required for all of those different components of our workflow. And if you now go to ECMWF and you ask around, like, where could machine learning potentially be useful, then you will come up with a lot of answers. And actually, I've done this, and I've basically collected all the different boxes that are above and below the workflow, and each of those boxes basically representing one of the application areas where we think machine learning is important. And the color coding corresponds to the color coding of the workflow tools. And what you should basically see is there are a lot of applications for machine learning that seem to be very promising for us, and also they're distributed all over the workflow. So wherever you go, you will find potential application areas for machine learning. And it's now up to us to really explore the space and to really understand which of those applications will really be changed by machine learning, and where we can really make a benefit from machine learning beyond the state of the art of the conventional tools, and for which of those application areas basically conventional tools maybe still continue to be better in the future. So we are in the process of preparing tools for operational use. And if you do so, you're kind of hitting a couple of challenges. One of the big problems that we have in operational weather predictions is that our tools need to be always reliable. So whatever you want to do, whatever you want to bring into a new operational weather forecast cycle, it needs to be reliable in a sense that it should not crash, for example, for unknown reasons. And it should always produce the same quality of results to some extent. So what this means is, if I'm basically suggesting a new tool for operational use, and it's put into the system, and then it will crash in the middle of the night, I may actually get a phone call to kind of get up in the middle of the night and try to kind of suggest a correction that the operational forecast can go out, because it's really important for us that twice a day our operations goes out to the user. And this basically means that there's a lot of doubt in the community to some extent towards machine learning tools, because machine learning tools are based on black boxes, and domain scientists don't like black boxes. So actually, we will need to convince the community that what we do with machine learning towards operational use is actually useful and also understood in a sense that we can trust the tools. The second problem that comes up is that we have new model cycles that we're developing. So typically we have 2 cycles a year, for example, and then if we develop a very great machine learning tool for 1 cycle, and we have a lot of data available because we have used the cycle for a long time, and then a new cycle is coming up, a new model version, then we basically need to retrain our machine learning tools for the new cycle. And this can be quite challenging if you, for example, only have like half a year of data available to retrain a tool that you have used, that you have originally trained from 10 years of data. So there's a challenge to actually understand how you can, for example, use transfer learning and these kind of tools to actually really make sure that your upgraded cycle is always producing the same quality of results for machine learning tools. And then the third thing is that we also have a lot of compensating errors in our models. It's not only us, it's basically whenever you look into weather and climate models, you will see compensating errors. And what this means is that, for example, if you had a small error in the cloud parameterization scheme, it could well be that the developments in the radiation parameterization schemes could make up for those small changes in the cloud parameterization schemes. And even though the result is going to be without the error, actually it's right for the wrong reasons, and we have compensating errors in the parameterization schemes. And we have no idea yet what all of this means if you kind of now introduce machine learning tools into this mix. So if you, for example, do bias correction and you correct for errors of a certain scheme, and then you use this for 10 years in operational cycles, you can have all sorts of ideas how this could actually harm you when you're using when you're kind of developing compensating errors over time as well. So there are a couple of things that we really need to be careful about. And the big thing that we're kind of really scared of is extrapolation. So we all know that like learning tools like deep neural networks don't like to extrapolate. And if we use operational predictions, for example, you may at some point run into weather situations that you have never seen before. And then you have to extrapolate, and we don't know exactly what the machine learning tool is going to do then. So that's a big problem for us, and therefore it's worth for us looking into this. And the question is whether knowledge-guided machine learning can help here. And obviously the answer is yes, but at least we kind of want to identify how big the problem actually is and how much we can kind of benefit from using knowledge-guided machine learning here. So let's ask the question, how bad is it if you use extrapolation? So basically, we want to train now a machine learning tool in a changing climates. And obviously, I know that Pierre has already talked about this and gave you very good examples, but still, I'm going to study it in a little bit more detail. And to do this, I'm going to look into a very simple model. So I'm going to really look into the smallest model that I can find, which is the longest 63 model. And the longest 63 model is nothing but a system of 3 differential equations that you can see on the left here. And if you kind of run it forward, you will see this famous butterfly pattern that is basically used to study chaotic behavior, because this is kind of one of the smallest systems that you can get that is actually producing chaotic dynamics. So let's have a look at this, and let's have a look at extrapolation. And to do this, we are going to look into 2 different systems. One of them is that we're going to produce a forecast based on a kind of a standard learning technique, which is the echo state network. In our case, it's basically fairly similar to a neural network, but it's not quite as sophisticated if you want. But we actually know from a couple of publications that the echo state network is producing really good results for this toy model, for toy models like Lawrence 63 or Lawrence 95. And then we also have a domain-driven regularization regression technique. And what this is basically doing, it assumes a certain amount of terms that could be included in the model. And then you basically perform regression to learn the coefficients in front of the terms. And by doing this, you basically learn the differential equations if you want. And so the idea is now that we run a model trajectory forward in time over a long period of time using a fairly precise time-stepping integration technique. And then we basically use those machine learning tools to then just try to learn the differential equations and learn how the system is progressing with those 3 degrees of freedom. So we're using, as I said, one learning technique, the echo state network, and one regression technique, which we call the D2R2. So let's have a look. If you just learn the Lawrence 63 model as is, and I do realize that this is not the nicest plot ever, and you plot the forecast error in this one here on the y-axis, and you have the time on the x-axis, what you basically, you get obviously growing error. It's a chaotic system, so you will always see errors growing over time. And the blue line here is what we get for the best performing echo state network, and the green line is what we get for the regression technique. And what you should take away from this is basically that the Lyapunov time is somewhere around here. So basically, the models perform actually quite well learning the system, because at the first Lyapunov time, the error hasn't really grown to a large extent. So that's good news. So all methods perform reasonably well. And now let's just assume that we're basically training for a different climate than actually our system is later applied to. So let's just assume that today's climate is just the left lobe here. This is not an error in the picture. It's just me cutting out only the left lobe for visualization. And we just use this data of the one left lobe for training. And we assume that climate change is kind of kicking us into a kicking point, and then we basically will end up with a two-lobe regime for the climate in a changed climate at the end of the simulation. So what's going to happen now? We also can increase the amount of training data that we get from the right lobe here. So we can kind of just use 1, 2, or 5% of the right lobe data and include this into the mix of the training, and see what's going to happen for the two different methods. So on the left side, you see the forecast error for the echo state network. And what you should see is that basically the error is kind of quite drastic if you only have a very limited amount of information for the right lobe. So if you only take 0, 1, or 0.1 or 1% of the training data from the right lobe, you will basically get very significant errors. And only if you increase the amount of data that you have for the right lobe to something like 10%, you will get better results. And well, you get much better results, obviously, if you kind of take the full data from both lobes. And the regression technique, on the other hand, is actually requiring only much lower amount of data from the right lobe. So even for 0.1% of the data from the right lobe, you're already performing reasonably well. And then if you increase to 1%, you're kind of really getting quite close already to the training situation where we had both lobes available. So basically, the echo state network performs quite horrible unless you provide something like 10% of the data of the right lobe, while the regression technique needs only a very small amount of data to perform well in the system. And also, the previous plot was about forecast error, and this plot here is now what we call the Wasserstein distance, and this is basically climate information. So you basically perform a very long simulation, and then you look at the PDF and you compare the different PDFs of the simulations against the truth. And what you see here is the x-axis is again the percentage of the data that you have available from the right lobe, and the y-axis is the Wasserstein distance, and the higher the number, the worse. And what you see is that the regression technique is actually performing quite well, even for just if you have no data whatsoever from the right lobe, while the echo state network requires something like 10% to perform well, and before it's actually quite bad. So the bottom line of this kind of little adventure here with the Lorentz 63 model is that regression techniques work quite well, actually. And this makes sense because basically they are learning the equations literally in terms of the physical sense. You can really literally get the equations that you've learned, the equation from the Lorentz 63 model out of the regression technique that you have learned. And therefore, the regression techniques are also able to kind of represent physical knowledge. So if a domain scientist would tell you that he would come up with a couple of terms, for example, that are physically meaningful in the system, you can use the regression technique to learn those terms, and you would be much better off. So this is an example actually where physical knowledge can help, and this is mostly done. I should really say mostly work done by Ryan Pyle and Ankit Patel at Rice University. So that's a good sign, a good sign that knowledge-guided machine learning can really help. And obviously, it's kind of also a great idea if you think about the communities. So at an operational weather center like EasternWF, we also have the problem that machine learning is kind of a bit of a different way to work than domain sciences, with earth system science as a kind of the standard domain, with where really most of the people really love physical knowledge and physical intuition. And if then the machine learning scientists come along and just kind of introduce some data methods, it's often a little bit tricky to kind of communicate between the communities. Whereas knowledge-guided machine learning is obviously great to kind of bring the communities together. It's also a great way to improve models and to take them, like to make them more resilient against changes. And for example, Pierre has given really great examples where knowledge-guided machine learning helps. And also on the bottom line is also, it's a great topic for writing research proposals at the moment. But it's getting quite late here in Germany, so kind of to keep awake, I thought also I should be a bit more controversial here in this talk. So I'm also going to add a couple of points where it may not be so great. And one of them is actually, if you think about methods that scale well to high performance computers, knowledge-guided machine learning may not be as efficient as kind of, well, standard techniques. And also, if you think about the magic of machine learning, so if you kind of think about using extremely complex machine learning tools with millions, if not billions of degrees of freedoms, then knowledge-guided machine learning tools may actually kind of come to the limits as well. And why am I saying all this? Because some of those things are kind of quite close to my heart as well. So I'm the coordinator of the Milestone project, where we really try to build machine learning tools that run well on petascale supercomputers. And every constraint that you have and kind of build into the system is often a problem for your scalability. So I'm not saying it's not possible. I'm just saying that we should really take care also and really develop also knowledge-guided techniques that can scale very well and make use of this amount of data. So basically, the question is, to some extent, to me, can we perform ablation studies, for example, using kind of some very complex transformer networks with unit structures and whatnot, all the magic of machine learning, with 10 millions of degrees of freedoms and trained from terabytes of data? Because if we can't, we're losing something. So please let me know what you think about this, and I would be very happy to discuss. Another point is also that often conservation properties are really important, obviously, and they also kind of really a good way to kind of talk to domain scientists. But the truth is also that in weather and climate models, most of the conservation properties are actually not conserved down to machine precision anyway. So for example, energy conservation and momentum are not conserved in any of the weather and climate models that I know. So the question comes up to some extent like, well, do we actually need always all the conservation laws that are given? And if, for example, our energy cycle is kind of repeating the atmospheric energy every 20 days or so, we can actually live with some sort of error in the energy. So it's not always true that we need to conserve all the properties. And also, and that's the last point that I'm going to argue against knowledge-guided machine learning in a knowledge-guided machine learning conference, is whether you can actually also, sometimes you can also develop techniques in machine learning techniques in a way that knowledge-guided machine learning may not be so important after all. And I'm not saying this all of this to kind of to say knowledge-guided machine learning is not useful. On the contrary, I've kind of just given you an example with the Lawrence 63 model, where I really show that it's really important that we should follow up looking into these. But let's just focus on the one on the last point, where I just wanted to give you an example where knowledge-guided machine learning may actually kind of be intrinsically included in a different way than to what we've seen so far as I can tell, which is on the preconditioning of linear solvers. So if you build an atmosphere ocean model and you do this in grid point space, you want to work with very long time steps, because otherwise you're not efficient. And if you do so, you often have to use semi-implicit time stepping schemes. And if you do this, you basically have to use a linear solver. And those solvers are very expensive because the state is very large. And the efficiency of those solvers critically depends on the preconditioner that you're using. So the preconditioner is basically trying to approximate the solution that you get from the linear solver. And if you have this approximation, you can offload some of the work for the linear solver and iterate for a smaller number of time and get benefits. And Jan Akman has now looked into the question whether you can use machine learning for preconditioning in this case. So whether you can try to predict the result of the inverse of the matrix that you need to kind of solve the linear system. And he's doing this on a global shallow water model with 5-degree resolution. And he's actually getting quite good results. So on the left side here, you see a case where we run the linear solver and the iterations that we need. And the residual is plotted on the y-axis. And the black line here is basically the point where you're good enough and you can stop the solver. And this is typically reached after something like 12 iterations. And if you now use a machine learning preconditioner, you have only 7 iterations. So the number is smaller and actually you're much more efficient. And also you're getting quite good results in comparison to the implicit Richardson preconditioner, which is a standard technique to be used there. The iterations here are even smaller. It's only 4 iterations, but the implicit Richardson is also more expensive than our machine learning preconditioner. So the method is actually working, but also the method is quite resilient because you basically still have the solver after your iterations with a machine learning tool. So the solver would still take care of problems that you get in the technique. And you can also be sure that the residual calculation of the solver will actually tell you if something is fishy is going on. So they're also kind of, well, ways to avoid knowledge guidance if you want, and also make use of machine learning. Another thing that I wanted to talk about is also a little bit of hybrid modeling. So we also looked into the emulation of parametrization schemes that Pierre looked into, and we've done this for the radiation scheme, and we didn't really get very good results yet for the pure emulation of the radiation scheme. So we could still see differences, and this is work ongoing, and I'm confident that we will soon crack the nut. But so far, we always get like some degradations in the quality of the forecast if we use emulators for the radiation scheme. But then we got the idea, or people like Robert Pincus actually suggested us to look into a different way of radiation scheme emulation. So what we do now is that we don't try to predict the entire tendency that we get out of the radiation scheme, but we're basically looking into the difference of the triple cloud scheme, which is used for operational use at ECWF, and the solver called the Spartacus radiation scheme. And here we basically can take three-dimensional shapes of the clouds into account, which we can't do in operations for the triple clouds. This is not, Spartacus is not used operationally because it's just too expensive for operational use. So the question is whether we can emulate the difference between triple clouds and Spartacus and basically save this kind of amount of computational time that we have, but still get good results and get the three-dimensional cloud effects included in our calculations. And David Meyer from the University of Reading looked into this, and they actually get quite good results. So in the plots here, you see the heating rates across the latitude and also in the vertical direction of the atmosphere model. And on the left, you see the heating rate for long wave and short wave that we get out of the difference from Spartacus and triple clouds in the real systems, in the real parametrization schemes. And on the right, you see the effect that you get from the neural network, and you basically see the effect is very similar in both cases. But the neural network is really kind of very, very cheap in comparison. So Spartacus is 4 times more expensive than triple clouds, which means it's too expensive for operations. But the neural network is basically extremely cheap, and we can certainly afford something like this as an increase in computational cost. The question now that comes to me is like, is this actually knowledge-guided machine learning? I don't know. I mean, we don't really do a lot of magic here. We just kind of switch from a signal to the delta to get better results. And can you extrapolate this? I don't know as well. I mean, basically, you still get problems, but the only difference is that the signal is smaller, so extrapolation may not be so harmful. I'm not going into detail here because Imi is already appearing on my screen, but I'm just also wanted to say like, oh, she's disappeared again, so I have another 5 minutes. No, I just wanted to say that post-processing, for example, is also a good way where you don't need to care too much about knowledge-guided machine learning, for example, because errors are not going to accumulate over time. Just 2 words, we are in quite exciting times at the moment in Europe because we have a couple of big projects coming up, and one of them is the so-called Destination Earth project, where we try to build digital twins of the Earth with very, very high resolution simulations, and there are going to be plenty of machine learning applications, I'm sure, in this framework of the project, just to get rid of the amount of data that we're going to produce. And there's a lot of scope for like investigations into knowledge-guided machine learning as well. So they're exciting times at the moment. So these are the conclusions, and I kept them very general, so I leave them for you to read, and I thank you for your attention.
Thank you, Peter. And you cut a little bit into your question and answer time, but you also asked so many questions yourself. I would love to throw half of them back at you some other time, probably.
Yeah, please do.
Especially the transformer and ablation studies. But anyway, let's go to the question that I hear in Slido. So first question, you mentioned reliability providing forecasts. Operationally, how does that work with a forecast of opportunity where some periods are more predictable than others?
Yeah, I mean, yeah, that's a good one. I mean, basically, whenever we put something in operations, we will test it on a lot of forecasts. I mean, we will have hundreds of forecasts run already before we actually put something operationally. So that it's not that we expect something totally strange to happen, but from time to time it does. I mean, from time to time a model can crash that has been run for, and we find a bug that has been there for 20 odd years or something like this. So it can, yeah, weird things can happen in chaotic systems of this dimensionality.
All right, thank you. Next question. In Pierre's talk, he mentioned adding conservation laws only resulted in going from n to n-2. Wouldn't that still allow for machine learning magic?
Yeah. Obviously, I mean, I was trying to confront you guys, and obviously there are methods that scale fairly well. I'm just saying that I would really like to see knowledge-guided machine learning applications within the next 3 years and a transformer network with 10 million degrees of freedoms.
All right, you just wanted to provoke us a little. Okay, next question. Do you think KGML stuff, for example, operator learning, is useful to operational machine learning?
Yeah, absolutely.
Well, that was a quick answer. So with that, we have 1 minute left. Anything else you want to say before we go to the break?
Okay. You wanted to throw questions back at me, but no, not really. It's late here in Germany already, so.
All right. So we give everybody an extra minute. Actually, now it's exactly 5 minutes past. So we will see you again in just 5 minutes. So time to stop so that people get 5 minutes time. And we'll see you after the break. Thank you. Bye.
Thank you.
Okay, that was a pretty short break, but we're ready to roll again here. Can everybody hear me?
Yep.
Yes.
Great, thank you. Okay, so welcome back, everyone. We are going to continue with our session on weather and climate. And our next speaker is Antonius Mamalakis, who is a postdoctoral researcher at Colorado State University. And Antonius is also going to continue with the tradition that we've already seen in all of our talks today of really bringing together these worlds of machine learning and climate science, but here's going to talk to us about some attribution benchmark data sets to help us realize when these tools are useful and maybe when they're failing us. So with that, Antonius, take it away.
Thank you, Libby, for the introduction. Welcome back, everyone. And I would like to thank the organizers for the invitation. It's been a great experience so far, and I'm looking forward to all the talks in the future. So I'll be talking about explainable artificial intelligence methods and how we need to introduce objective frameworks to assess their performance. And I'm hoping to make two clear arguments with this talk. The first is that there is an actual need for this objectivity in assessing these methods. And the second aspect of the talk is that I will be offering one way to do it, and that is by benchmarking these methods with data sets where we know the explanation, how the explanation should look like. So this slide aims at making clear why we actually need objective frameworks to assess these methods. And what you are looking at here is an example from an image classification task. This has been published by Adebayo et al. In 2020. And what the authors have done here is that they have trained a convolutional neural network to classify different pictures. And you're looking at a specific example here of a junco bird, where the network has successfully classified this picture as a picture illustrating a junco bird. And then the authors wanted to look into the network and use different XAI methods to try and gain insight about what features in the input were the most helpful, the most important features for the network to successfully classify this picture. And there is no, actually the point of this slide is not, there's no need to know the actual details of each method shown here, but the point I'm trying to make here is that applying different methods can lead to vastly different answers. And so, for example, here you can see that some methods highlight the eye of the bird as an important feature, whereas some other methods highlight different features in the body, over the body of the bird as important features for this classification. And so this can be very problematic. This uncertainty in the explanation can be very problematic because in a climate prediction setting or in an application in geosciences, we need to know actually with quite high certainty what was the features in the input that led to a correct prediction. And so the uncertainty in the explanation propagates into uncertainty and low trust about the model itself, the neural network itself. And that's why we need objective frameworks to be able to assess these methods, gain insights about their weaknesses, strengths, and be able to know under what circumstances which methods are more suitable to use. And so I'll be offering here a way to do that. And this way is by using attribution benchmarks. Now, attribution benchmarks are essentially synthetic data sets, which consist of a synthetic input and a synthetic output, where the explanation, the attribution of the output to the input is already known. So these data sets are designed in a way that we know already the explanation. I'm providing here results for a climate prediction setting. So this data set is inspired by a climate prediction setting. And what I have done is, as a first step, I have created a synthetic series of synthetic fields from a multivariate normal distribution. And these fields are supposed to represent SST anomalies, for example. And so each map here represents a month of SST anomalies or independent time scale. This is arbitrary. And then I pass this input through a nonlinear function f, which I know, and I create a scalar value for each that corresponds to each sample. So this function f transforms each map to a scalar value, which is supposed to be the output of this synthetic system. And this way I create the series of the predictant variable, which could represent precipitation anomalies, for example. Now, this function f, I have to say that is, for this specific example, is the summation essentially of local nonlinear responses across the globe. So for each grid point here in the globe, imagine that there is an underlying nonlinear function that transforms this input value into a local response, and then I'm summing up all these local responses to get a scalar value. So in the third step, then, which this is where things get more interesting, I pretend that I don't know this function f, although obviously I do, and I train a neural network to approximate this function f. So this is why I'm labeling here this neural network as a function f hat, if you will. And this network is trained to predict the y values given the x. And because this is a synthetic framework, I can create as many samples as I want. And in this case, I have created 1 million of those. So in this way, I can achieve a high prediction skill and almost perfect, if you will, training of the network. And this allows me to assume that I have very closely approximated the true underlying function. So the assumption here is that this function f hat is very closely similar to the function f. It's not identical, but it's very close. So having established that, then I can use different XI methods and test how well they explain the network, because I know the function f and I can derive the ground truth of the explanation. And by comparing the ground truth to the results from the XI methods, I can assess their efficiency. And that's the whole concept. And so we'll start seeing some technical details here now. So I'm using a fully connected neural network to approximate, to train and be able to predict this synthetic output. I'm using, as I said, 1 million samples, and 900,000 of these samples are used for training. 100,000 of these samples are used for testing. Now, we have achieved a very high prediction performance, which is 99% in terms of coefficient of determination. This means that the network can actually capture 99% of the variability in the Y series in the testing data, and this is considered quite sufficient, quite high performance given the nonlinearity of the problem. We are not arguing here that this is the optimal architecture to address this problem, but because to keep things as simple as possible, and because the performance is already high, we stick with that. The XAI methods that I will be using are shown here. I'll be using 6 different methods. 2 of them estimate sensitivity, 4 of them estimate attribution. And these are equally valuable things, but we will clearly show in the next slides that they are different things. The method gradient is a method that essentially estimates the local gradient of the local sensitivity of the output of the network with respect to the input, to the different input features. And so it's a way to estimate the sensitivity of the network. And the smooth gradient, this is the second method, is a method quite similar to the gradient, but it's supposed to be a more robust method, because before estimating the gradient, we apply numerous perturbations to the input, and that by averaging out the gradient along all these number of perturbations, we are able to essentially account for the noise. Then four methods estimate attribution. Input times gradient is the first one. This method is essentially doing what the name suggests. It's simply the multiplication of the gradient, of the local gradient, with the input value. And the second method is intergradient gradients here. This is also pretty similar method to the input times gradient, with the difference that here we estimate the gradient by over many different points again to get a more robust picture of the gradient. These different points are located in along the line of the input and the reference point. This reference point can be the zero vector or a gray image, for example. The last method that I will be using is the layer-wise relevance propagation. This method applies, considers the output of the network and then propagates back the prediction to lower layers. In this way, by propagating back the prediction and ultimately reaching the input space, in this way we are able to assess the importance of each input feature to the prediction. Now, there have been many propagation rules to do that. The LRPZ rule is one that I'm considering here. And the LRP alpha beta rule is a second one. I'm not going to go into details about what exactly these propagation rules are doing, but I will simply mention that the alpha beta rule, for the alpha beta rule, I will be using a value of 1 for alpha and a value of 0 for beta. And let's now go see some results. What I'm presenting here is, I'm focusing on a specific sample from the testing data that I have created. And for this specific sample, the Y value, the true Y value is 0.066, and the network predicted 0.0802. Now, what you're looking at in this map is the ground truth of the attribution. So pixels that are highlighted in the red color correspond to pixels that positively contributed in this Y value. And pixels that are highlighted here with the blue color correspond to pixels that negatively contributed to this value, meaning that if it were not for them, this Y value 0.066 would have been even higher. And so now the goal is to apply different XAI methods and find out which pixels help the network to predict a 0.0802. So the first two methods that I'm using here is the gradient and the smooth gradient. And quickly you can obtain that these two methods do not provide consistent results with what the ground truth shows. For example, here over the Eastern Tropical Pacific or the Southeastern Pacific, these both methods highlight pixels with a negative sign, which is opposite in the ground truth. Also, for the tropical Atlantic, pixels are highlighted here in the two methods with a positive sign, which is opposite with what happens in the ground truth. And also, simply correlating the two maps, you can see that these two methods provide results that do not correlate with the ground truth. And what I'm showing this result here to clearly illustrate that these two methods, because they estimate sensitivity, and sensitivity is not the same as the attribution. That's why exactly they don't correlate with the ground truth that we have. The next two methods, input times gradient and integrated gradients, these two methods actually do very well. You can spot here the positive contributions of pixels in the Eastern Tropical Pacific. You can spot the negative contributions in the tropical Atlantic and in the Southern Atlantic. All these are consistent with the ground truth. You can see over the Southern Indian Ocean, these methods, both of them return positive contributions, as is also the case for the ground truth. So these two methods actually provide consistent results. The correlation is pretty high. It cannot be one because, again, the network is not identical to the true underlying function that we have used to create this synthetic dataset. LRP alpha 1 beta 0. Here you see an interesting result. Although this method highlights pixels which are actually important for the predictions, it assigns the same sign to all the pixels. So according to this method, all the pixels in the world contributed positively to the prediction of the network, which is clearly not true. And so we need to keep in mind that this method is likely to do that, to mix the positive and negative contributions. And lastly is this LRP-Z method, which is also doing very well and is very consistent to the ground truth. And if you look closely, you will see that it's identical. These results are identical to the method input times gradient. And the reason is because I'm using a rectifier network in this study. And there is proof that when this is the case, these two methods, input times gradient and LRP-Z, are equivalent. Another thing I want to mention just by looking at this slide now is that, again, if we didn't have the ground truth, if that was a real problem and not a synthetic one, we wouldn't be able to actually be certain about what the network does, because applying different methods, we get all different answers. And so this is why it is important to have objective frameworks to assess these methods. A second example here from the same data set, we can get pretty similar insights as the previous slide. The gradient and the smooth gradient, these two methods do not correlate with the ground truth. The methods input times gradient, integrated gradients, and LRP-Z, all these three methods are very consistent. And the LRP alpha 1 beta 0 again provides results which assigns the same sign to all the pixels. And this can be an issue in a real application. So this is the last slide, I think. How am I doing with time?
You have about 1 minute until questions.
Okay.
So you're doing great.
Yeah, thank you, Libby. So in this slide, what I'm doing is essentially I'm trying to convince the audience that the insights that we got in the previous slide are not case dependent. These insights are valid for the whole data set. And so what I'm presenting here is the correlation coefficient with each method, with the results of each method with the ground truth. You can see clearly that the gradient and the smooth gradient do not correlate with the ground truth. There is a correlation of 0 on average. The input times gradient, integrated gradients, and LRP-Z for this specific setup here and for this specific model are the most consistent methods. And And also I want to highlight that, again, the LRP alpha 1 beta 0 propagates the sign of the prediction back to the input, and this makes it likely to mix the positive and negative contributions. So we need to keep that in mind. And lastly, the two key things that I want to leave you with is that we need to create objective frameworks to understand better these methods and gain insight about their strengths and weaknesses, as we saw clearly. And a way to do it is by constructing data sets where we know a priori the explanation. All these results have been posted in a paper into arXiv, a paper written by myself, Ima, and Libby. So anyone who is interested can look into more detail in this paper. And now, yeah, I will be taking. I'll be happy to take questions. Thank you.
Thank you, Antonius. All right, so you've got a few questions here. So the first one, can you define what precisely counts as success for attribution?
Okay, so yeah, that's a great question. Attribution is essentially correct. Success for an attribution would be to correctly identify the pixels that positively or negatively contributed to the response of the system for a specific response of the system. This is different than the sensitivity. Sensitivity is simply the sensitivity by changing the output, what is the effect of that change of the input to the output. So this is where these two things are different, but they are equally important. So as long as we have different ways to explain a network, but as long as these methods provide exactly what they're supposed to be providing, then all these are equal. Sensitivity and attribution is equal important.
So spinning off of that, there was another question about, is there a relationship between sensitivity as measured, for example, by the gradient, and it's, what's the relationship between sensitivity and attribution? And then they ask, in this context, do we know what true sensitivity is?
So yeah, I mean, the sensitivity and attribution are not the same. Sensitivity is essentially, if we think of the neural network as a function, sensitivity is the gradient at a specific point. Attribution is if we had many predictor variables contributing to the value of that function. Attribution is how much of each predictor is contributing to the value of the function. So in other words, it can be that a predictor is a function is highly sensitive to a specific predictor, but that doesn't mean that this predictor at a specific point is contributing too much, and vice versa. So they are not the same thing, but they are equally, at least in my mind, they are equally important to know.
So here's an interesting one that was just added. Could this work be extended to understand whether certain climate problems or applications are harder to use an XAI method for attribution on? So rather than it sounds like rather than compare the methods, can you sort of compare the problems?
Oh yeah, definitely. That's actually, yeah, that's actually very interesting. Very interesting. The only thing that I want to highlight with that is when you create new problems, it is always under this concept that I introduced here, it's always the case that you need to make sure that you can objectively derive the ground truth of the attribution, because otherwise it's not fair to compare or benchmark these methods to something that is inherently not derivable. So that's why I have used at least as a first study here the summation of local responses, because by definition, when you sum up things, it's each one its predictor how much it was contributing to the output.
Thank you so much, Antonius. And feel free if there are any extra questions to answer them in Slido. And Tim, I'll pass it to you.
All right, thank you. It's my pleasure to introduce the next speaker, Laurie Trenery, who is an assistant research professor in the Department of Atmospheric, Oceanic, and Earth Sciences at George Mason University. And with that, I'll let Lori take it away.
Thanks, Tim. All right. Can everybody see my screen?
We can, but it's not in full screen mode, so it doesn't matter if you're in full screen or not.
Oh, okay. Well, it looks full screen to me. Anyway, hello, everyone. It's great to be here. My thanks to the organizers for inviting me. So this work was done in collaboration with my colleague, Tim Del Sol. And we were really interested in understanding how we might utilize climate model data to inform our prediction, subseasonal prediction of observations. So just to clarify what I mean by subseasonal timescale, and also why it's such a challenging problem. This figure is showing some qualitative measure of predictive skill on the vertical axes and predictive lead time on the horizontal axes. On the far left are weather events.
Lori,
Yeah.
I'm going to interrupt because we can't see anything but your first slide right now.
Oh, really? Okay. Let's.
Okay, now we can see.
Huh? It must be the going into full mode. I'll just leave it like this. I think it's the same issue that you had earlier.
Yes.
Okay, so back to my point here. So what is subseasonal timescales? So on the far left, we have weather events, and those are forecasts that are targeting hours to 2 weeks, has relatively high skill initially, and then the skill drops off rapidly at 2-week time period. So these forecasts are often referred to as initial value problems. They get their skill from the initial conditions. And then on the other end is seasonal outlooks or seasonal forecasts. This is typically targeting periods between 3 months and 12 months. They're often referred to as boundary value problems. And as an example, if we have an El Nino that's developing in the tropical Pacific, those evolving SST patterns are associated with well-known atmospheric circulation patterns. So we might expect above average temperatures in certain regions and below average temperature in other regions. And nestled in between those two timescales is a subseasonal timescale. For this particular talk, I'm meaning prediction that's 3 to 4 weeks in advance. So they're often considered, it's a difficult time scale to predict because it's considered too long to benefit from the initial conditions, yet relatively short to benefit from the slowly evolving boundary conditions. So despite the difficulty in making these predictions, there's tremendous societal value. There was a historic heat wave, for instance, that hit the Pacific Northwest, and this map is just showing the temperature anomalies. And you can see that there were 20°C temperature anomalies extending from British Columbia all the way down into Oregon. And associated with this heat wave are impacts across many sectors of society, human life to agriculture and wildfire. So if we can advance our capabilities to make accurate subseasonal predictions, we could minimize the cost of human life and also minimize the impacts to these other sectors in society. So given the societal benefit, there have been initiatives to improve subseasonal predictability. And one such initiative is directed towards improving the numerical models. And there are two main programs, S2S, Subseasonal, the Seasonal Project, and SubX. And both were really focused on evaluating the subseasonal skill and operational forecasts, and then using that information to somehow improve the numerical models. And this example, this figure is showing an example of the skill in terms of anomaly correlation for two operational systems on the left and right, and a persistence benchmark in the middle. And you can see that the operational forecast systems are doing better than the benchmark, but the correlations are still between 0.2 and 0.3. So, at best, it's explaining almost 10% of the variance. So there's room for improvement. And so another line initiative is developing empirical predictions. And as Tim mentioned in his introduction, the Bureau of Reclamation partnered with NOAA establishing the subseasonal forecast rodeo, and they provided forecasts for week 3, 4, 5, 6, temperature and precipitation in the Western US. And here I'm just showing some skill results from the inaugural winners in highlighted in orange, and the benchmark. So that was the currently used operational forecast by NOAA, the CFSV2 and damp persistence. And you can see over the forecast period that they systematically outperformed the CFSV2. So this study really established unequivocally the utility of using machine learning methods to advance our subseasonal predictive skill. And so we're also interested in utilizing some of the same tools that Huang et al. Use, but we're going to take a step back, and we're interested in understanding what processes are contributing to that predictability and how the sources of predictability vary in the CMIP, in the climate models, and how they compare with observations. So to do that, we're going to develop some empirical forecasting models, and we're going to train on and predict observed temperature using the CPC data. And our predictors are only going to be SST. We're limiting our predictors to SST because they're considered variations in SST are likely to make a big contribution to predictability in our target region. And it's easier to understand if we isolate our predictors to one variable. So, and we're only analyzing the period 1982 to 2019. And then we'll develop another set of predictive models that are trained on the CMIP-6 data. Again, we'll use the surface temperature data and SSTs as predictors. We're training our empirical forecast models on the pre-industrial control runs. We're doing that to minimize, to take out the impacts of external forcings. These are things like greenhouse gas, anthropogenic aerosols, ozone. And so the values are fixed to 1850. And we're going to concatenate the output from the 13 models that are listed in this table. So we'll have 6,898 years of data to train our model. And then this model will then be used to predict observations. So why are we using the CMIP-6 data? Well, part of our goal is to understand what the processes are that are driving subseasonal predictability. And we also then want to compare those processes with observations. And so we know that if we can fit and train a model on the CMIP-6 data, and we can skillfully predict the observations, then we know that that skill is actually coming from the dynamical models. And that then demonstrates that the processes contributing to the predictability are consistent between the observations and the dynamical models. So prior to training our models, process the data, so our forecast will only target the months December through February. We do this because that's when we expect the predictability to be greatest. All the predictors and predictands are 2-week averages, and the seasonal cycle is removed from the 2-week averages, so the data are centered. And if for observations, we detrend the data to remove the impacts of external forcing like greenhouse gases. And as I mentioned earlier, we're targeting weeks 3, 4. And so as an example, if we're targeting the 2-week average between December 1st and the 14th, our predictors would be the 2-week average between November 4th and the 17th, excuse me. So our forecast region is the same that was used in the subseasonal forecast rodeo at the Western US. We'll make a prediction at each one of these grid points. We'll have a total of 499 stations that we're making a prediction, and all the data are regridded to the same 1x1 degree grid. As I mentioned before, our predictors are SSTs. It's likely that local SST variations as well as large scale variations will impact predictability. So our predictors are constructed in such a way to capture both aspects. So in red and in green, we have our local predictors. So these are individual grid points. And then the blue and the black are representing the Pacific and the Atlantic basins will capture the large scale variations. And in total, we'll have 356 predictors. So to capture the large scale variations, we're going to project the data onto the eigenvectors of the Laplacian operator. This is just another way of decomposing the data into large-scale modes. And here I'm showing an example of, for the Pacific, this is the second and third Laplacian. The first Laplacian is the basin mean. So most of you are familiar with decomposing the data using EOFs. This is just another way of decomposing the data, but it doesn't depend on the data set. So we always have the same basis function and associated time series with each pattern. So it allows us to compare like to like. We'll use a hierarchy of statistical models. So our first empirical model is a benchmark, and it's expected. So the El Nino has the largest impact on seasonal predictability. It's likely to also have a big impact on subseasonal predictability. So our benchmark forecast will be a prediction. It's an ordinary least squares prediction where we estimate our betas by minimizing the cost function listed here. Our y's are the grid point temperatures. And our X or predictors is the Nino 3-4 index. We'll combine that with two lasso configured models. The first is a single task lasso. And we're minimizing now to find our betas, we're minimizing a cost function that's similar to ordinary least squares, but we've now included this penalty term. And so this penalty term is included to penalize model complexity. So as lambda gets big, it goes to infinity, these betas will go to 0. And conversely, as lambda goes to 0, this cost function will approach ordinary least squares. And the second lasso model that we'll use is multitask. So in the single task, we're fitting the lasso model grid point by grid point, and no predictive model knows anything about its neighbor. In multitask lasso, we're minimizing a cost function of this form to get our regression coefficients, and this y is now a matrix. So we're minimizing the cost function with respect to all the grid points. So I just want to clarify how we estimate our predictor or regression coefficients and select our lambdas. So we have our benchmark, regression coefficients are estimated from observations. And then we have our two sets of lasso models. So we have an observation trained lasso models. The betas are estimated from the first 18 years of observations. And then we select lambda through a 10-fold cross-validation. And then we have our CMIP6 trained models, and they're trained on, the betas are estimated by training on the CMIP6 data. And then we use the first 18 years of observations to select lambdas. So in this way, the observations are actually informing the predictive model that we've estimated from the CMIP6 data. And all the lasso models are evaluated on the same 19-year portion of observations. So the metrics that we will use to evaluate our forecast and verification data are centered, so the time mean has been removed, and we'll look at the normalized mean square error, which is essentially the variance of the errors to the variance of the verification data. If the mean square error is 1 or greater, that's a bad forecast. And also the correlation coefficient. So we're looking at how well in phase the forecast and verification data are. So now we can look at the overall assessment of these statistical models. So in terms of the average temporal correlation, so averaging the correlation across all of those 499 grid points, and versus each empirical model on the horizontal axes, and then this black horizontal line, it denotes a 0 correlation. For the lasso models, I did a sensitivity evaluation to see how the performance of the model changed if I swapped the roles of the training and evaluation data. So there are red and blue indicating that there are different data were used to train the lasso models, and this was kind of to see how robust the fit was and how sensitive it was to data. And so you can see that our benchmark forecast in an average sense, the correlation is negative. It's not doing particularly well. And then if we look at the observation trained models, they also show a great deal of sensitivity to the training period, as does the CMIP6 multitask. And in fact, the most robust and best performing model was actually the CMIP6 trained single task models. For that reason, we'll focus the rest of this presentation, we'll focus on this particular model. And for comparison, we'll compare it with that when we derive the same single task model from observations. So this now we can start looking at the skill. So the figure at left is, so these are both correlation maps. The figure at left is the correlation map that we get from the CMIP6 trained empirical model. At right is for the observations. The red colors denote positive correlation, which is what we want, and the negative shades denote the blue shades denote a negative correlation. So you can see, looking at the CMIP6 trained model, that there's positive correlations over most of the region, and with the exception of in the interior, and it's close to 0, and there are some negative values. If we compare that with our observation trained model, we see that the positive correlations are kind of limited to the Pacific Northwest, and there's large regions of negative correlation. I performed a field significance test on these two patterns, and I was established that the CMIP6 correlation map is significant, while the observation correlation map is not. So one of our questions was to try to get out what are the processes that are contributing to this predictability. And one way you might infer that is by looking at the relative frequency in which the predictors are selected by Lasso. And so this figure at left is showing the relative frequency that each one of our predictors is selected for the CMIP6 trained model, and at right for observation trained model. And you can see that from the CMIP6 trained data model, that the Pacific really has a large number of those single predictive models are selecting some of the predictors from the Pacific, and to a lesser extent, the Atlantic. And if we compare that with what we see in observations, you can see that the predictability is sort of spread, the predictors are sort of spread across all of the predictors. And we believe that this is largely because there was so much more data that went into estimating these regression coefficients, so they're much more robust. In this, when we do our observation trained models, there's only 18 years of data, or 18 years of 2-week averages. So in the first figure that I showed for our results, we looked at the average correlation, and the correlations varied, and in cumulative sense, they were weak. Another way we can look at this is in terms of the mean square error. And at the beginning of this talk, I said if the mean square error is 1 or above, that's indicative of a low skill forecast. So here I'm now showing the average normalized mean square error for our different empirical forecast models. The horizontal line shows the 1, and you can see that all of the forecast models have low skill in terms of the normalized mean square error. Even our best performing model is hovering near 1. So the question that we have then is, if you have low skill because you're fitting these predictive models at each grid point, does that really mean that you have no skill at all? Because we're considering climate, we would expect that if you have predictability, it should be associated with a large scale feature. And so what we're going to do then, when we have a skillful forecast, we want to minimize the mean square error. And so and essentially what we have is a ratio of variances, and we can show that this can be reformulated in terms of an eigenvalue problem. So now we're trying to find the combination of forecasts and verification data that minimize the mean square error across all of our stations. And when we do that, so that's what our Q vector is essentially finding, that linear combination. This is our eigenvector. The gamma gives the eigenvalues. which is the normalized mean square error. And just a quick comment, I know I'm running out of time here, so that these covariance matrices are estimated across the station data, but because there's 499, that would make these covariance matrices 499 by 499, it's quite large. So I reduced the dimension by projecting the data onto the Laplacian operators. So now they're 50 by 50. So associated with each of so when we do this decomposition, we're finding the most skillfully predicted large-scale patterns. And associated with each pattern is a time series, which we can get by projecting the data onto the eigenvectors. And we can get the regression patterns by regressing the data set onto that time series onto the data set. And we'll estimate significance with respect to a bootstrap. So here I'm showing the normalized mean square error versus truncation. The red line shows no skill. And then the eigenvalues are given in black. And you can see that there are two modes that are well separated from no significance, the no significance threshold. And so we have identified a large scale pattern that is being predicted by our individual models. And so here, what do they look like? And these are estimated from CMIP6 data. And they're typified by a dipole and temperature that's oriented sort of north to south. And if, for those who are familiar, you might recognize that as an ENSO-like pattern, where we, during winter, we kind of have this canonical teleconnection pattern where the warmer temperatures in the higher latitudes and cooler temperatures lower latitudes. So the next question that we have is, so those results were estimated from the CMIP6 data. Now, how does that compare to observations? Because that was part of our goal, is to see how that compares with observations. And so I've repeated the CMIP6 map at left and the observation estimated map at right. You can see they're both characterized by dipoles and temperature, but their orientation is different. So are they in fact different? Because remember, at observations, I only have 18 years of data. So I went back to the climate model data and I picked a random model, the GFDL ESM4, and I sampled it to have the same equivalent size as observations and would estimate these maps. And here I'm showing two examples on the middle and the right. And you can see that the middle pattern somewhat has some similarities to the observed pattern, and the pattern at right is more consistent with the overall CMIP6 derived pattern. So we can't say that the observation, while it looks different, we can't say that it is in fact different, because it appears that the most predictable structure appears to depend on the data. So now, recall that we had pretty low correlations when we looked at the cumulative correlation. Yes, thanks, Tim. Now we've found this large scale pattern that's predictable. And essentially when we do this eigen decomposition, it's effectively filtering the noise and isolating that predictable structure. And so we have this eigenvector that is going to combine those forecasts to give us that predictable feature. So we can apply it to observations and correlate the forecast. So we're trying to see if the forecast is predicting that large scale pattern. Is that what those individual grid point forecasts is trying to do? We determine that by projecting the forecast and the verification data onto these eigenvectors. And this is the leading component. The observations is shown as a horizontal dash line. You can see that it's much higher if we're looking at this large scale pattern. And then I looked at how the skill compares in the individual models. And I sampled the model data to have the same length as the observations. So for each model, the asterisk denotes the mean of the distribution of these correlations, and the bars are giving the 5th and the 95th percentile. I just wanted to see if they were consistent with observations, which they are across all the climate models. And moreover, the models are consistent with each other. So I'm running out of time. Get to my last point, and then I'll open it up for questions. But the idea was we started out wanting to know where the predictability was coming from. We identified these large scale features that seemed to have structure that was similar to Enso teleconnection pattern. Now we have this time series that's capturing the variability of that predictable feature. And so I can correlate that, or I can regress that the SSTs onto that time series and look at what the structure of the SSTs looks like. And here is the CMIP6 derived at left and observation derived at right. And you can see that the feature that really jumps out at you is the SST anomalies in the Pacific. They look very ENSO-like. And so we can conclude that, and these are features that are robust and similar between the two data sets. So with that, I will go ahead and end my talk because I'm already going over, but hopefully you see the utility of using the CMIP6 data to train predictive models and to predict observations, and then also how if we isolate this large scale patterns, we can enhance our predictability. So thank you for your attention.
All right, thank you, Laurie. Unfortunately, we are out of time. We don't have time for questions.
Oh, wow.
But the great thing about this format is you can go to Slido and you can reply to the individual questions. And we are trying to leave those replies up for a little while before the next speaker. So you can try to do that. So I'll now hand over the moderator to Libby.
All right, and our final speaker after an awesome day, I would like to present Pedram Hazanzadeh, and he's an assistant professor at Rice University, and he's been doing lots of work, again, with the weather, climate, machine learning world. I feel like every few days you guys have a new paper coming out that I have to read. This is part of my motivation as I get it straight from the source here. So thank you, Pedram, for wrapping up a great day.
Okay, great. First of all, I'd like to thank the organizers for this great workshop, and also I'd like to thank the audience. I know it's probably late in the day for some of you. So today I'll tell you briefly about some of the work that we are doing on building physical constraints into neural networks for weather climate modeling. And specifically, I'm going to talk about our work on subgrid scale modeling or closure modeling that the team and Pierre nicely talked about in the earlier presentations. And the test case that I'm going to use is two-dimensional turbulence. It's a rather simple, it's a toy model. It still shares some of the key characteristics of turbulence in the atmosphere and ocean. And I think it's still some of the work that I present here is going to be applicable to problems more broadly in weather and climate modeling of turbulent flows, and multi-scale nonlinear systems. The work that I'm presenting is mostly from a work that is led by Yifei Guan, who is a postdoc in our group at Rice. So we already had a lot of great presentations, so I'm going to very quickly go to my introductory slides. So as you know, simulating weather and climate system is complicated. One of the main reasons is that we are dealing with a multi-scale system. This cartoon here just reminds us of the broad range of length scales and time scales that we are dealing with and in the atmosphere alone. Even though in many problems, we are mainly interested in what's going on in the large and with the large and slow variables that collectively I'm going to show with variable X in the next few slides, we also cannot ignore what's going on at the smaller and faster scales, which I'm going to collectively show them with variable Y. Now, as you know, the traditional approach to deal with these kind of multi-scale systems has been to use a coarse resolution numerical solver to solve the governing equations that are closed in the large scale variable X. We can solve this, for example, in climate modeling on the resolution of around 100 kilometers. But then we will need closure, as Tim already discussed. We need basically parametrization for subgrid scale processes, everything below the resolution of the numerical solver. And so basically, generically, I represent that with field function P that we basically for the larger scales, for the resolved scales, we can basically calculate what the effect of the smaller scales are. And these are called parametrization. And there has been decades of work on physics-based parameterizations for various processes. There has been a lot of progress, but it's still clearly we need better ones to better do climate projections and predict extreme events. So in the past few years, there has been a lot of interest in what machine learning can do. And one way that some studies have looked into, what machine learning can do is to basically use machine learning to learn this relationship, to learn a closure between the resolver skills and basically the subgraded skills. You might use machine learning to estimate some of the key parameters in a current parameterization, or what I'm going to focus on is basically when we do what I call non-parametric data-driven parameterization, or DDP, where you don't assume anything about the structure, about the functional form of how X and Y relate to each other, but leave that to a neural network. So like many problems in applications of machine learning to weather climate modeling, once we figure out what is the specific application, let's say it's non-parametric DDP, there are still a lot of questions and challenges, and many of them actually opportunities that we have to address. We have to basically figure out what is the machine learning method to use, how to deal with the problem that we don't have high quality data in many of our problems. So we are in the small or poor data regime. How to incorporate physics or some of the properties of the equations that we know of into the neural network, how to deal with interpretability, generalization, which here specifically I'm talking about extrapolation, as already we heard about this from a number of talks. For example, if the forcing on the system increases, or if you think about the turbulent flow, if the Reynolds number increases, how to deal with this extrapolation problem. And at the end, we might build a good neural network that does well offline, but then when we couple it with the numerical solver, many studies have seen basically instabilities. So my group has been working on each of these items for the past few years, but today I'm first going to talk about this issue of instability, where we try to use some of the domain knowledge, basically in terms of backscattering analysis, which is looking at inter-scale energy and entropy transfer to look at this problem of instability. I'll talk about some of our more recent work on incorporating physics by using physics-informed architectures and physics-informed loss functions, particularly to deal with the small data regime. So we are building symmetries, some of the conservation laws into the neural network. And as you will see, it helps in the small data regime. And even though I don't think I will have time, but I'll very briefly mention some work that we are doing on using transfer learning to enable neural networks to do extrapolation. So the system that we are using is two-dimensional turbulence. The governing equations are simply this equation for vorticity, omega, and a stream function psi. This is the Jacobian, the nonlinear term. This is the Reynolds number. This can be a forcing on the system. For now, we assume that there is no forcing. And here I'm showing you an example of a direct numerical simulation, which basically at a given Reynolds number, like 32,000, if you have enough resolution, for example, around 2,000 Fourier modes in each direction, we can solve these equations without any further approximation. And here we have started with a specific initial condition that had a specific energy spectrum. And then we let the system run. And at some point it comes to self-similar regime. And that's where we do our training and testing. So now let's say we can't do DNS, it's too expensive. And we want to look at basically what's called large eddy simulation. When we take these equations and we filter them. So here over bars, basically it means a filter and coarse graining. We can just use a simple Gaussian filter or a box filter, anything like that. And we know that, again, Tim already talked about this, we can almost write our equations in terms of the result value, the filtered variables, but we'll see that there would be a residual term that looks like this. And I'm going to call this term pi, which is basically the divergence of the stress tensor. This is where the effect of the turbulent eddies are, and this is the SGS term. So obviously there is an advantage in looking at LES compared to DNS in terms of computational power that you need. We can easily, for example, at this Reynolds number, reduce the resolution by a factor of 8 in each direction. We can take larger time steps. So already a factor of 640 fewer degrees of freedom that we can use in LES simulations. But then the challenge is how to represent pi only in terms of the result variable. So we can close these equations. Again, it's the major problem. And there has been a lot of work on this. Maybe one of the best known work actually developed for weather forecasting was by Smokorinsky, where you can, for example, assume that pi is just diffusive, so that basically the turbulent eddies are just going to do diffusion. So you can basically use eddy viscosity times the Laplacian of omega, and this is going to be the parameterization. So what we are trying to do now is to basically lead that to a neural network to learn this relationship between pi and the result variables from DNS data, and then we couple it with this LES solver and see what happens. And most of what I'm going to talk about is already in this beta. It is available on archive. So again, there has been a lot of work on physics-based models, but one major problem with physics-based models is that many of them only account for diffusion, and they do not account for what's called backscattering, or that you can think of it as like anti-diffusion. Just to demonstrate this issue, let's define a subperiodic scale transfer function t that I define as pi times Laplacian of omega bar. Notice that for models like a Smagorinsky, or here I'm looking at a more basically modern version of it called dynamic Smagorinsky, if eddy viscosity is positive, which is what's used in practice, t is always going to be positive, which basically means that again the eddies only do diffusion. So, but let's see if that's always true or not. So here is an example of the filtered vorticity field from the DNS simulation. So the box here in the second row, you kind of see this zoomed in. This is what the filtered DNS gives us. So this is, you can treat this as the truth. And you see that a lot of grid points, they are red, if you zoom in as well. So this is the forward cascade. This is the grid points when we have diffusion due to the smaller scales. But also you see that there are a number of grid points, and not small, there's a good number of them, that it's blue. And this is where you have backscattering. This is when the unresolved scale, where the smallest scales is actually forcing the resolved scale. And again, you can think of it as anti-diffusion. This is something that is known that in modeling of the atmosphere, in modeling of ocean, modeling of a lot of the fluids, is actually something that physically exists and is important. But many physics-based models do not account for it because it can lead to instabilities. For example, the Smagorinsky model, as you see here, it's all red. It only does diffusion, which is very good to stabilize a numerical solver. But again, it doesn't take care of all the physics. So what we want to do is that, particularly we want to see whether, especially non-local, non-parametric DDP, for example, using convolutional neural networks, can do this basically better, can account for both diffusion and backscattering and correctly. I'm not going to go through the details of the CNN that we are using, but this basically has 10 layers, 10 convolutional layers. The input is the filtered stream function and vorticity, and the output are those pi terms. For now, we start by using a simple loss function and basically MSE that is shown here. I emphasize that for now, the architecture of this neural network and the loss function, they are both physics agnostic. There are also other things like it's deterministic, it doesn't account for memory, but those things can be added to it later. But let's see what we can do with this physics agnostic CNN. So first we look at what's called a priori or offline test. So here, this is, again, the truth from filtered DNS. This is what our CNN does on the same sample. You see, if you look at the whole domain, or if you can let this zoomed in part, it does a great job in capturing all these scales, whether they are doing backscattering or forward transfer. This is also another neural network. This is just a MLP feed-forward network from another paper that had been already published in JFM. And you see that this one is local. So it does basically look at every grid point. This one also does a pretty good job if you look at the smallest scales, capturing both backscattering and diffusion. And then these are just for specific samples. We can look at the average of pattern correlation between the true pi terms and the predictions from the machine learning method. And the physics-based model will see that the machine learning methods have much higher pattern correlations, averaged over hundreds of samples compared to these physics-based ones. But we know that this is not the whole story. For example, in this paper, what they found was that if they couple these ANN with their basically correlation solver, it blows up. So what they did, it has been done in many studies, is to take this and wherever it does anti-diffusion to kill that. And so the model becomes diffusive, it becomes stable. But again, you lose some of the advantage of what you we're hoping to get from a data-driven approach. So in our work, we wanted to see whether with our CNN, we can get a stable, basically parameterization without doing anything. And one thing we did, we started looking at how this depends on the number of training samples. So N here, this is the number of training samples. We look at the training samples from 500 to 50,000, and we look at that pattern correlation. We'll see that even with 500,000, we have a pattern correlation of 0.78. And basically, with 100 times more data, it gets to 0.93. But also here in the last row, I show you basically the fate of a simulation, a coupled simulation. We couple this CNN with the coarse resolution solver. And we'll see that even for a case when this pattern correlation is 0.9, we get instability. And only when we get to around 0.92 that we get a stable data-driven parametrization. So then what we did, and maybe this is the first kind of knowledge guided thing that we did, is that we look at this C separately based on the grid points that do diffusion versus backscattering. And we found something that I think is sort of interesting and can be informative, and that is the diffusion, even with a small number sample, has been already learned well. You start with a pattern correlation of around 0.84 with 500 samples. And with 100 times more data, you increase this correlation by basically around 0.12. On the other hand, for backscattering, with a small training set, you start at around 0.5. But then, as you increase the number of samples, you get to around 90. And so it seems that backscattering, and these are the two conclusions we drew from this, is backscattering is harder to learn data when the training set is small. And also we speculate that this disproportionately low accuracy for backscattering is the reason for instabilities. And again, this is for this system, but backscattering had been known even for physics-based systems to cause problems, something like to capture, but then because it is forcing the system, if it's not captured accurately, it basically can cause instabilities. So after that, once we realized how to build basically a stable data-driven parametrization method, we found that when we couple this and look at the online mode, the results are actually pretty good. These are like basically comparison of the filtered DNS, which again, you can look at it as consider it the truth with what the CNN does. The patterns look pretty good, much better than like the physics-based models that are very diffusive. You get better results in terms of short-term forecasting. And also, you can look at the statistics, you see a clear advantage. For example, here I'm showing you the turbulence spectrum. Here, the solid blue line, that's the CNN, and it matches better than any of the other methods with the filtered DNS. And maybe the PDF of vorticity, looking at this tail, that's the best place to see the advantage of using a CNN. That is the solid blue line. It matches pretty well with the tails of the vorticity of the PDF with the FDNS, with the filtered DNS. On the other hand, these other methods, they're all pretty diffusive. So they might capture the bulk of the PDF rather okay, but they miss these extreme events. So this is what we have done so far, again, with the physics agnostic neural network. More recently, we have been looking at basically a force system, and we add a forcing at different wave numbers, and also we add linear damping. And so here we can basically generate at the given Reynolds number, we can generate different kind of flows when they have forward cascade versus inverse cascade. They can have different scales when we do the simulation. So providing basically different test cases to look at what we do. And again, for all of these, we can build a stable, accurate LES for a range of parameters with 500 samples. Now, you might notice that 500 samples, this is much lower than that 50,000 sample. One thing I want to say is that it's just the same data, except that here we have basically we reach the interval of sampling. So there's one thing that many people ask, well, how much data do you need to train a neural network, for example, for subgrid scale modeling? And I think the answer is not just a single number in terms of the number of training samples, but the correlation, the inter-sample correlation also matters a lot. So here again, it's the same length of data, but with the basically increase the sampling rate, we still can get accurate results. But what we wanted to do next was to see if we build physics into the neural network, whether we can decrease that number from 500. And so we started looking at what the physics agnostic CNN might be missing. And get rid of this. So, and there are at least two things we came up with. One was, okay, anyway, so one of the things, like we started by doing a simple experiment, which is we generated a dipole that is shown here. Now, dipole would just move around, and we can calculate the filtered DNS of this and train a CNN, and the CNN would work pretty well. But let's say that we look at the sample that is this 90-degree rotated. Now, probably you and I look at this and say that, okay, the pi term should also be rotated by 90 degrees. We know some of the properties of the subgrid scale term. On the other hand, now if you put this into the CNN, the physics agnostic CNN, it would produce this. And then you realize what the CNN is doing. The CNN looks at this and see that it came here. And what it does, it basically takes this, or this and puts it on this side. And because this went here, it takes this part and put it here. So the CNN basically does translation, but doesn't understand that this is a simple rotation. So of course, if you have a lot of data, if you have seen this and this, whichever you see later in the testing, it would work well. But it's a problem if you do not have a lot of data, if you are in the small data regime. Another problem with the physics agnostic CNN is dealing with some of the conservation laws. For example, you can show that because the nonlinear term only redistributes entropy, but doesn't basically produce it, or it's not a sink of entropy, that basically a domain average variable like this should be conserved. So you can think of, well, I like my, whatever comes out of my CNN to have the same domain average omega bar times pi with the FDNS. Now, we can look at this error, the error of basically this, when you have 50 samples, training samples versus 2000. And you see that here the error is 17%, here the 10%. The 7% difference might seem small, but actually it basically makes a difference in the terms of the stability in the online testing. I'm not showing those results, but this one blows up and this one is stable. So we came up with 3 remedies for this. So in the next couple of minutes, I'll try to quickly go through this. One is data augmentation, which is if you know some of the symmetries in your data, for example, you can take this and rotate it by 90 degrees, 180, 270, and have all these as the inputs to your data. And it's called data augmentation. That's been used in many studies in the past. Or you can just use something like an equivariant CNN, that some of the symmetries or really equivariances are built into the neural network. The difference between this approach and this one is here, I have the same filters, I'm rotating the input, but what something like a group CNN does, it takes the same input and rotates the filters. And finally, as you can guess, you can just build this entropy constraint as a self-constraint into the loss function. And we have done this, and these are some of the offline results. I'm not going to go through the details. One takeaway from this is if you have a lot of data, which are here, if you have 2000 samples, adding physics doesn't help a lot. But if you do not have a lot of data, for example, if you have 50 samples, then you will see that these spaces that have some sort of physics baked into them do much better. And again, it's just a matter of 0.1, 0.2 in correlation, but that has a huge impact on the online performance. So here you get a big gain by adding physics in the small data regime. I'm not going to show the online results because of time, but you will see this effect of building physics in the small data regime into the accuracy. We also had done this building physics into the neural network in terms of symmetries. In the past, we have a paper that is in GML about using data assimilation and using a transformer. And you can see, again, advantages there in terms of better capturing wave breaking and things like that. But again, I'm not going to talk about. I'll mention that we have a lot of success with using, okay, so I'm moving too fast. It's the last point I want to make. Using transfer learning, we have a bunch of papers on showing that for a chaotic system, if you increase the chaoticity or if you increase the Reynolds number, you can basically close the generalization gap and do some sort of extrapolation, even by a factor of 100 in the Reynolds number. So for the interest of time, I stop here. I should say that there's a paper that I've contributed to, but it's really led by Kartik Kashinats on physics for machine learning for weather climate modeling that has 10 examples of doing different things of building physics into the neural network that you might want to check out. So with that, I stop here. I'll just leave it here, and I'm looking forward to questions.
Thank you, Pedram. So I don't see any questions. I will note we have 2 minutes left just because we started a tiny bit late for you. So if anybody has questions, put them in Slido. I have lots of questions, but I will restrict myself to one. So actually, this is a bit more general. Stepping back, at near the end, you showed a plot showing how for small sample sizes, adding the physics in helped it a lot. But if you have a lot of data, what do you need? It'll learn the physics, or what do you need physics for? My question is, from like a domain science perspective, is there anything to be learned by looking at what it was about the constraints that allowed those smaller sample sizes to still do as well? Does that make sense? To actually go in and try and understand why incorporating the physics when you did at those smaller sample sizes helped it learn faster? Does that make sense?
Yeah, I think there would be a lot of, if I understand your question, if your question is to then kind of dissect the neural network and see what changes was made, then sure, I think there can be a lot of value there to know how to better enforce those. Again, currently we are trying to see what has been done in machine learning in terms of equivariant neural networks or things like that, and none of them were designed for example, looking at Rossby wave breaking and better capturing that. But I think something that better guide us, I think that can be very, very helpful. Maybe something related to that, what we are doing is we are trying to understand what happens in transfer learning. Because in transfer learning, you only retrain 1 or 2 layers out of 10 or more. And actually, we have some results about this that we are working on writing up, that you can see some understanding of how the weights, for example, change. And I think if we can do that without the needing of actually some data from a more complicated system, that can be extremely useful. So, and maybe some of the methods that you have been working on, I think can be useful for this kind of understanding.
Great, thank you so much. And look at that, we're perfectly on our time here. So thank you so much, Pedram, for finishing our whirlwind of a day. And thank you everybody for joining us for day 1 of our 2nd workshop on knowledge-guided machine learning. I don't know if there are any other announcements to be made other than, if so, jump in. Other than we'll start again tomorrow for day 2. So thank you, everybody.
Thank you.